हमारे साथ जुड़े हुए हैं प्रोफेसर शंगी साहब। वो काफी मैराथन साइकिलिंग चलाते हैं, मतलब कहना नहीं चाहिए, पर उनकी एज 55 प्लस होते हुए भी वो 51 किलोमीटर की साइकिलिंग भी कर लेते हैं और बहुत रिकॉर्ड टाइम में अपने यंग लोगों के साथ बराबर, मतलब वीक में मेरे ख्याल से हर वीक चलाते हैं वो 100 किलोमीटर के आसपास, और जब भी इनकी साइकिलिंग की वो होती है उसमें जरूर। और पार्टिसिपेंट से मैं ये भी शेयर करना चाहूंगा कि हमारे जो आर्ट ऑफ लिविंग के सीनियर फैकल्टी मेंबर्स आज जुड़े हुए हैं, जैसे पारस कौली जी तो पिछले 18 साल से आर्ट ऑफ लिविंग के प्रोग्राम्स कर रहे हैं, सिखा रहे हैं लोगों को, और राजस्थान में तो लोग इनसे बहुत परिचित हैं। श्रेया अग्रवाल जी और कोहली जी और इनके और साथी लोगों ने हमारे 3 साल से स्टूडेंट्स के लिए स्लैब प्रोग्राम किया है, और हफ्ते भर का कई बार 3-3 4-4 बैचेज भी किए हैं 60-60 स्टूडेंट्स के। तो इससे उन सबको बच्चों को हैप्पीनेस और मतलब योग प्राणायाम के अतिरिक्त भी काफी सारे सौहार्द, परस्पर सौहार्द की चीजें सिखाई हैं उन्होंने, उससे काफी फर्क पड़ा है। मैं इनका बहुत आभारी हूं, और राजस्थान टेक्निकल यूनिवर्सिटी इनकी इस मामले में बहुत कृतज्ञता है कि ये हमें जब भी हम इनको रिक्वेस्ट करते हैं सहर्ष तैयार हो जाते हैं। कल याद मतलब मैंने 8 तारीख को इनको रिंग किया, तुरंत वो उन्होंने कहा आप तो डेट बताइए हम आ जाएंगे। तो मैं इनके साथ बहुत बहुत साधुवाद इनका हमारे प्रति स्नेह का।
सर आपका सौभाग्य, सर ये हमारा सौभाग्य है कि आप हमें अपॉर्चुनिटी देते हैं कि स्टूडेंट की लाइफ में हम कुछ कंट्रीब्यूट कर पाते हैं, उनके बेटरमेंट के लिए कुछ अपना योगदान दे पाते हैं। थैंक यू सो मच अग्रवाल सर, राजस्थान टेक्निकल यूनिवर्सिटी, इस अपॉर्चुनिटी के लिए।
हमारे साथ उदयपुर सीमेंट वर्क्स के डॉक्टर एस.बी. हेगड़े साहब जुड़े हुए हैं। मैं उनका बहुत इस सेशन में स्वागत करता हूँ। गुड मॉर्निंग सर। मॉर्निंग सर। हम दिन भर तो सीमेंट कंक्रीट की बातें करते हैं, थोड़ी देर आज हम स्वास्थ्य की बातें भी कर लें, अपने मानसिक स्वास्थ्य और शारीरिक स्वास्थ्य की बातें।
बिल्कुल बिल्कुल।
हमारे साथ कई स्टेट्स के लोग जुड़े हुए हैं, जैसे अभी पुसात्का जी ने ज्वाइन किया, ये नागपुर में है प्रोफेसर।
गुड मॉर्निंग।
मॉर्निंग पुसात्का साहब। अगर कोहली साहब और श्रेया जी, क्या ये हम बताना चाहेंगे आप लोग कि आज आप क्या हमें किस तरह से गाइड करना चाह रहे हैं?
जी सर। तो सर shall we start the session?
माथुर साहब, अनिल माथुर सर।
हाँ सर ज्वाइन कर रहे हैं सर 2 मिनट में, है ना?
अच्छा अच्छा, जी सर, जब
अपन
तक
इनफॉर्मल बात कर लें सर, अभी ज्वाइन कर रहे
हाँ हाँ सर।
आज के सेशन में हम कुछ ज्वाइंट रोटेशंस प्रैक्टिस करेंगे और साथ साथ में ज्यादातर हम लोगों का बैठने का काम रहता है, तो कुछ टेस्ट ऑफ योगा हम लोग प्रैक्टिस करेंगे। और जब से ये कोरोना पैंडेमिक स्टार्ट हुआ है, ये कोरोना की वजह से ज्यादातर क्लासेस ऑनलाइन होती है, हमें ज्यादा टेक्नोलॉजी का यूज करना पड़ता है, जिसकी वजह से आईज पे काफी ज्यादा स्ट्रेन पड़ता है। तो आईज के लिए कुछ एक्सरसाइज हम प्रैक्टिस करेंगे कि आप अपनी चेयर पे बैठे बैठे, ऑफिस में बैठे बैठे अपनी आईज को हेल्दी रख सकते हैं, अपने नेक को, अपनी बैक को हेल्दी रख सकते हैं। ये हम प्रैक्टिस करेंगे। कुछ ब्रीदिंग एक्सरसाइज हम करेंगे कि कैसे हम अपनी लंग कैपेसिटी को बढ़ा के रखें, उसके बारे में बात करेंगे। इसके लिए कुछ प्राणायाम प्रैक्टिस करेंगे। और आज के सेशन को जो हम एंड करेंगे एक मेडिटेशन के साथ। वैसे तो आपको सभी को जानकारी है कि कोरोना पैंडेमिक के दौरान कहते हैं जितनी डेथ कोरोना की वजह से नहीं हुई, उससे ज्यादा डेथ सुसाइड करने की वजह से हुई। लोगों ने सुसाइड कर लिए, यूथ ने सुसाइड कर लिए, है ना। उसका एक ही रीजन था कि मेंटल स्ट्रेस। तो मेडिटेशन उसमें बहुत हेल्प करता है, कैसे हम स्ट्रेस फ्री रहे, माइंड को कैसे रिलैक्स रखें। तो ऐसी कुछ टिप्स, ऐसी कुछ टेक्निक आप लोगों के साथ शेयर करेंगे जो ऑलरेडी आपको पता है, बस आपको रिवाइज करवानी है, वो हम लोग प्रैक्टिस करेंगे। मेरे साथ श्रेया अग्रवाल है जो कि क्रेनियोसैक्रल थेरेपिस्ट है, और मेरे साथ सिद्धार्थ पांडे जी है जो कि बहुत सीनियर टीचर है आर्ट ऑफ लिविंग के। आज का सेशन की शुरुआत हमारे सिद्धार्थ पांडे जी करेंगे। आज का सेशन बीच में श्रेया जी हमारी जो क्रेनियोसैक्रल थेरेपिस्ट है, आईज के लिए और बोन्स के लिए कुछ टेक्निक हमें सिखाएंगी। यस श्रेया।
यस सर।
हमारे साथ सेंट्रल रोड रिसर्च इंस्टीट्यूट के भी विट्ठल साहब जुड़े हुए हैं। सीनियर फैकल्टी हमारे यहाँ की द्विवेदी साहब भी जुड़े हैं। इन सबका मैं स्वागत करता हूँ।
थैंक यू।
पार्टिसिपेंट्स की जानकारी के लिए बता रहा हूँ कि फर्स्ट डे के सेशंस के यूट्यूब लिंक आप सबको भेज दिए गए हैं। सभी सेशंस रिकॉर्ड किए जा रहे हैं और ये सेशन भी रिकॉर्ड किया जाता है। इसका भी हम आर्ट ऑफ लिविंग टीम से परमिशन लेके यूट्यूब पे डालना चाहेंगे, हमारे यूनिवर्सिटी के कंटेंट्स चैनल पे। We are just waiting for our Honorable Vice Chancellor Sahab to join. Whenever he joins, we will start the program.
प्रवीण जी।
हाँ सर।
प्रवीण,
हाँ
तो
सर।
सर को जीमेल वाला लिंक नहीं भेजा क्या, गूगल वाला? वो यूट्यूब खोल के बैठे हैं।
नहीं, यूट्यूब पे तो कुछ है ही नहीं सर। भेजा था सर, दोबारा मेल कर देता हूं।
वापस दोबारा मेल कर दो, है ना। हाँ सर, गुड मॉर्निंग।
गुड मॉर्निंग सर। सर नमस्कार।
सर आपका माइक अनम्यूट, माइक। गुड मॉर्निंग।
या गुड मॉर्निंग, गुड मॉर्निंग।
Honorable sir, we have with us Shri Paras Kohli ji, Shreya Agrawal ji and Siddharth Pandey ji from Art of Living sir. यदि आपकी परमिशन हो तो मैं पारस कोहली जी को
सर स्टार्ट करें?
या डेफिनेटली स्टार्ट करिए आप।
गुड मॉर्निंग सर।
गुड मॉर्निंग पारस जी, गुड मॉर्निंग।
तो माननीय कुलपति जी की परमिशन से आप कोहली जी प्लीज स्टार्ट करिए।
तो आज के सेशन की शुरुआत हम ज्वाइंट रोटेशन से करेंगे, बिकॉज आप देखेंगे जैसे जैसे उम्र बढ़ती जाती है तो हमारे ज्वाइंट्स बहुत ज्यादा पेन करने लगते हैं। ज्वाइंट रोटेशन मतलब ज्वाइंट्स में ग्रीसिंग का काम करने के बराबर है, एक तरह से ग्रीसिंग का काम करते हैं। तो आज की सेशन में ऐसा नहीं है कि आपको सिर्फ बैठना है और हमें सुनना है। इस सेशन में आपको पार्टिसिपेट करना होगा। क्या आप तैयार हैं इसके लिए? यस। हम साथ में पार्टिसिपेट करेंगे, सहभागी बनेंगे इस सेशन में। तो जहां कहीं भी आप बैठे हैं वहीं अपने स्थान पर खड़े हो जाए। एवरीवन प्लीज स्टैंड अप। और थोड़ा सा वार्म अप हम करेंगे, अपनी जगह पे टहलना शुरू करेंगे, थोड़ा चलना हम लोग स्टार्ट करेंगे। यस, तो खड़े हो जाए अपनी जगह पे। यस, और जहां कहीं भी है हल्का थोड़ा सा शरीर को ढीला छोड़ दे, दोनों हाथों को ढीला छोड़ दें, दोनों बाजुओं को ढीला छोड़ दें, चलना शुरू करें अपनी जगह पे। जहां कहीं भी आप है और अपनी क्षमता के अनुसार जितना आप आराम से कर पाए, कंफर्टेबली कर पाए, उतना ही आपको करना है। और चलें, दोनों हाथों को ऊपर ऊपर लेके जाएं, आगे की तरफ चलें, थोड़ा सा घुटने को ऊपर उठाएं, दोनों हाथ ऊपर, जंप करते हैं। इस कोरोना पैंडेमिक में जरूरी है कि हम फिजिकली हेल्दी रहे, हमारी इम्यूनिटी अच्छी रहे। फिर कोरोना जैसे वायरसेस कुछ भी हमारा नहीं बिगाड़ पाएंगे। सुबह सुबह सो के उठते हैं तो अंगड़ाई लेते हैं, वैसे अंगड़ाई लेते तो साइड में थोड़ा पीछे आगे की तरफ झुके, वेरी नाइस, पीछे आगे की तरफ अच्छे से स्ट्रेच हो जाए, ऐसे ट्विस्ट करें, ट्विस्ट योर वेस्ट, वेरी नाइस। आज के सेशन में हम प्रैक्टिकल तो करेंगे, कुछ चीजें सीखेंगे, साथ साथ में कुछ बातें भी करते रहेंगे बीच बीच में। तो आपका जो राइट हैंड है उसको आप सर के ऊपर ऐसे रखें। श्रेया, मैं प्रॉपर दिख रहा हूँ ना?
Yes, Paras sir, you're visible.
ओके,
हाँ सर, विजिबल।
तो आप अपने सर पे राइट हैंड ऊपर रखें और सर के ऊपर हथेली को आपको घुमाना है। जो स्कैल्प है उसको रोटेट करेंगे, हथेली के बजाय जो स्कैल्प है वो रोटेट होगा राइट टू लेफ्ट, अब लेफ्ट टू राइट, ऐसे। बहुत जरूरी है इसको एक्सरसाइज करना। एवरीवन पार्टिसिपेट। अब दोनों हाथों को साइड में ऐसे रख दें। अब यहाँ पे भी 5 टाइम क्लॉकवाइज, सुपर ब्रेन योगा में आता है, अपोजिट साइड, एंटी क्लॉकवाइज, वेरी नाइस। अब दोनों हाथ अंगूठा बीच में मुट्ठी बंद कर ले ऐसे, और अपने सर को टैप करें, टैप योर हेड, अच्छे से टैप टैप करें। वेरी नाइस। यू नो, अब दोनों कानों को पकड़ ले अपने, और कानों को बाहर की तरफ खींचते हैं ऐसे, वेरी नाइस। फिर नीचे, फिर ऊपर, मुस्कुराते मुस्कुराते, फिर बाहर की तरफ, फिर से नीचे। अब अपने ईयर्स को रोटेट करेंगे ऐसे। कहते कान खींचने से हमारा इंटेलेक्ट शार्प हो जाता है, ऑलरेडी आपका तो है ही। हमारी हर एक पनिशमेंट पूरा साइंटिफिक है। स्कूल में टीचर्स कान खींचा करते थे, अपोजिट साइड में, वेरी नाइस, वाह। अच्छा, कोई सामान कहीं रख के हम भूल जाते हैं तो हमारी उंगली यहाँ पे ऑटोमेटिकली चली जाती है, यानी कि यहाँ प्रेस करने से कुछ तो कनेक्शन है हमारी मेमोरी के साथ, तो यहाँ पे प्रेस करें। एक कुछ टेक्निक्स आप ऑफिस में बैठे बैठे कर सकते हैं प्रैक्टिस, एंटी क्लॉकवाइज, वेरी नाइस। अब हम करेंगे ज्वाइंट रोटेशंस, आईज के लिए श्रेया मैम हमें सिखाएंगी, और अभी हम ज्वाइंट रोटेशन करते हैं। यू नो, योग इज द कॉम्बिनेशन ऑफ बॉडी, ब्रेथ एंड माइंड। सांस, मन और शरीर तीनों को एक लय में लेके आना, एक तीनों को हार्मोनाइज करना, इसको योग बोलते हैं। तो सांस के साथ कोऑर्डिनेशन कैसे? सांस लेते हुए आपकी जो गर्दन है वो पीछे की तरफ, नेक पीछे जाएगा, जितना आप स्ट्रेच कर सकते हो स्ट्रेच करें पीछे, वेरी नाइस। सांस छोड़ते हो आगे, और चिन को चेस्ट के साथ टच कर दो, ताकि बैक साइड जो नेक का है वहां स्ट्रेच आए, वेरी नाइस। सांस छोड़ते फिर से पीछे, सांस छोड़ते सामने, चिन को टच करो, फिर से सांस छोड़ते पीछे, सांस छोड़ते आगे। अब नेक को स्ट्रेट कर देते और अपने राइट शोल्डर्स की तरफ देखें, राइट शोल्डर की तरफ। शोल्डर्स को रोटेट नहीं करना, सिर्फ राइट साइड देखो, लेफ्ट साइड, राइट साइड, लेफ्ट साइड, सेंटर में। अब हम अपनी नेक को रोटेट करेंगे 5 टाइम क्लॉकवाइज एंड 5 टाइम एंटी क्लॉकवाइज। सांस भरते हुए, सांस छोड़ते हुए, चिन को चेस्ट के साथ टच करें और सांस भरते राइट साइड से क्लॉकवाइज। आप देख सकते हैं सामने स्क्रीन पे, लेफ्ट साइड से सांस छोड़ते। टेक योर होल अटेंशन टू योर नेक एरिया। पूरा ध्यान आप अपनी गर्दन पे रखें। अपोजिट डायरेक्शन में करते हैं, एंटी क्लॉकवाइज। पूरा ध्यान आप अपनी गर्दन पे। हमारा ज्यादातर ऑफिस में बैठने का काम होता है, नेक को प्रॉपर एक्सरसाइज नहीं दे पाते, इस वजह से सर्वाइकल पेन होने लगता है। बहुत जरूरी है कि नेक को टाइम टू टाइम हम एक्सरसाइज करते जाएं। एंड रिलैक्स। अब दोनों हाथ आप अपने शोल्डर्स पे रखें, ऐसे शोल्डर्स रोटेशन करेंगे, ऐसे रखें। सांस लेते हुए अपने एल्बो ऊपर लेते जाए, सांस छोड़ते हुए आगे से। योग और एक्सरसाइज में यही डिफरेंस है। जब योग करते हैं तो बॉडी, ब्रेथ एंड माइंड हार्मोनाइज है। जब एक्सरसाइज करते हैं तब ऐसा नहीं है। इसलिए एक्सरसाइज करने के बाद हो सकता है आप टायर्ड फील करो, और योग करने के बाद आप एनर्जाइज और पॉजिटिव फील करते हैं। अपोजिट साइड में आपके कोई प्रश्न हो, यू हैव एनी क्वेश्चन, तो आप टाइप करके सेंड कर दीजिए। शोल्डर रोटेशन हो गया। अब बारी आती है एल्बो। तो दोनों एल्बोज को ऐसे फोल्ड कर लो, सांस लो, सांस छोटे। सभी लोग करें, वेरी राइट। अब दोनों हाथों को सामने सीधे कर दो, दोनों बाजुएं शोल्डर्स के पैरेलल बराबर में सामने। रिस्ट रोटेशन, कलाई को घुमाएं एंटी क्लॉकवाइज and feel the difference in your body. मुट्ठी को जोर से कस के बंद कर लो, tight your feet and relax. फिर से दोनों हाथ ऊपर और दोनों बाजुओं को ऐसे हिलाएं, रोटेट करें। सर्कुलेशन प्रॉपर हो रहा है बॉडी के अंदर ब्लड का। अपोजिट साइड में एंड रिलैक्स। अब साइड में स्ट्रेस आ जाता है, उसको रिलीज करते हैं। राइट हैंड ऊपर उठाएं और लेफ्ट साइड को 1 2 3 4 5 अपोजिट साइड करते हैं। 1 2 3 4 5 एंड रिलैक्स। अब स्टमक एरिया के लिए तो स्विंग करें ऐसे, पैर एक जगह स्टिल और पीछे की तरफ देखें, एकदम पीछे ऐसे। आप सामने स्क्रीन पे देख सकते हैं मुझे। मुस्कुराना इंपॉर्टेंट है, स्माइल रखनी है आपको अपने फेस पे, चाहे नकली क्यों ना हो। फेक इट टिल यू मेक इट एंड रिलैक्स। अब कमर के लिए कुछ के तो कमरे बन गए होंगे। अंगूठा सामने की तरफ, हथेलियां पीछे, स्पाइन को सपोर्ट करती हुई राइट और रोटेट करें। वेरी, हमें बहुत ज्यादा बैठने का काम होता है आजकल, फिजिकल इतना नहीं हो पाता वर्क, तो कमर में दर्द होने लगता है। तो बहुत जरूरी है कि हम कमर को रोटेट करें, इसके लिए एक्सरसाइज करें। वेरी नाइस। अपोजिट साइड करते हैं। 1 2 3 4 एंड 5। हिप ज्वाइंट के लिए तो आप चाहो तो सामने किसी वॉल है तो वॉल का सपोर्ट ले सकते हैं और सामने किक करेंगे ऐसे। वेरी नाइस एवरीवन। अपोजिट लैग। आप वॉल का सपोर्ट ले सकते हैं अगर आपको कहीं भी एंड रिलैक्स। अब करेंगे नी के लिए, तो हैंड्स ऑन योर नी, दोनों हाथ अपने घुटनों पे रखो, दोनों पैरों को पास में ले आओ। हमारे दोनों पैर ऐसे होने चाहिए, बिल्कुल ऐसे। नी को ऐसे बैंड करना, स्ट्रेट ऐसे। वेरी नाइस। अब नी को रोटेट करें। अच्छा होगा अगर आप सभी अपने वीडियोस ऑन कर ले, ताकि हमें पता चलता रहे कि आप क्या कर रहे हैं, अच्छे से कर रहे हैं कि नहीं कर रहे हैं। अपोजिट साइड। एंड रिलैक्स। अब लास्ट ज्वाइंट रह गया हमारा एंकल, तो राइट लेग ऐसे ऊपर उठाए, एंकल को रोटेट करते हैं एंटी क्लॉकवाइज। अगर आप चाहें तो अपनी वीडियो जरूर से ऑन करें ताकि हम आपको करेक्ट कर पाए, हमारे मेरे जो को टीचर्स है आपको चेक कर पाए। किक करें। अब लेफ्ट लेग। अपोजिट साइड। एंड रिलैक्स। ज्वाइंट रोटेशन हो गए। अब एक स्ट्रेच हम करेंगे जो ऑलरेडी आपको आता है। श्वास भरते हुए दोनों हाथों को ऊपर उठाए, ब्रीद इन, स्ट्रेच योर हैंड्स, दोनों हाथों को ऊपर इंटरलॉक कर लें, हथेलियां ऐसे छत की तरफ ऐसे, एंड स्ट्रेच योर होल बॉडी। यस। अब पैर के पंजे पे आ जाएं, लिफ्ट योर एंकल्स और सांस छोड़ते दोनों सर पे। फिर से एक बार स्ट्रेच योर होल बॉडी, स्ट्रेच स्ट्रेच एंड स्ट्रेच एंड रिलैक्स। अब साइड में सांस भरते ऊपर, पैर नहीं उठाना इस बार, दोनों पैर जमीन पर रहे, बराबर वेट, एंड स्ट्रेच योर लेफ्ट साइड। स्ट्रेच स्ट्रेच। अपोजिट साइड स्ट्रेच करें एंड रिलैक्स। और जहां कहीं भी आप खड़े हैं वही अपनी जगह पर बैठ जाएं। अब हम आईज के लिए कुछ टेक्निक प्रैक्टिस करेंगे।
So settle down wherever you are. अपनी अपनी जगह पर बैठ जाएं. If you are sitting on chair, sit comfortably, easily. जब हम स्क्रीन पे देखते हैं और कंटिन्यूस हमें स्क्रीन यूज करना पड़ता है तो हमारी आईज पे बहुत स्ट्रेन होता है, और वही स्ट्रेन हमारे हेड पे, सिर पे दिखाई देता है। कई लोगों की शिकायत होती है कि सिर दुख रहा है, या फिर बहुत ज्यादा स्क्रीन देखते तो हेडेक होने लगता है, हेड हैवी होने लगता है। इट्स जस्ट बिकॉज वी आर स्ट्रेनिंग अवर आईज. So we'll do a very small exercise which you can do whenever you're sitting in your office, yes, you're working or anything, right? So sit straight, spine erect. So first I will demonstrate. मैं एक बार थोड़ा सा बताऊंगी, फिर उसके बाद we all will practice. So our eyes, our optic nerves are connected to the back of our head. हमारे आंखों की optic nerves हमारे back of the head से connected हैं. So one hand we'll keep at the back behind, and one hand covering our eyes, right? We'll cover our eyes with the other hand. First, before covering your eyes, just see what you have to do, right? So first we will blink our eyes, and there will be 3 rhythms in blinking our eyes. So first we'll blink our eyes very fast, blinking, keep blinking. We'll blink our eyes fast. Then we'll blink our eyes very in a medium pace. Open, close, open, close, open, close, open, close. And then it will be a slower pace. Open, close, open, close, open, close. So this will be the activity of our eyes when our hand will be covering our eyes. हमें अपनी आंखों को, पलकों को झपकाना है जब हमारा हाथ अपनी आंखों पे होगा. एंड मैं पूरा गाइड करती रहूंगी. सो आई होप एवरीवन विल बी विद मी. सो वन हैंड बिहाइंड योर हेड, एक हाथ सर के पीछे. वन हैंड कवरिंग योर आईज. नाउ स्टार्ट ब्लिंकिंग योर आईज फास्टर. Keep blinking your eyes faster at a very fast pace. Keep blinking. Blink your eyes faster. Faster. Keep blinking. Keep blinking. Keep blinking your eyes in a faster pace. Now medium. Open, close. 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 Now slower pace. Open, close. Open, close. Open, close. Open, close. Now we'll do 2 more rounds of these 3 cycles. Keep blinking your eyes in a faster pace. Now start blinking your eyes in a faster pace. Keep blinking. Blink your eyes. Blink. And if possible, keep your attention at the back of your head and keep blinking your eyes. Faster. Now medium. Open, close. 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 Now slower pace. Open your eyes. Close. Open. Close. Open. Close. Open. Close. Open. Close. Now again with the first faster pace, keep blinking your eyes. Start blinking. Keep blinking your eyes in a faster pace. Blink until you feel that there is some heaviness in your eyes. Blink. Keep blinking. Now medium pace. Open your eyes. Close. Open. 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 Close. Now slower pace. Open. Close. Open. Close. Open. Close. Open. Close. And now relax your hand. Keep your eyes closed. We'll take 6 to 7 long deep breaths. Breathe in. And breathe out. 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 One last time. Breathe in. And breathe out. And whenever you feel complete, you may slowly and gradually open your eyes. So, how did you feel after doing this small exercise? Anyone would like to say?
First time did this and felt very good.
Great. Anyone else?
It was extremely relaxing. In fact, the people like us working for companies would love to do this every day. Thank you.
Yeah. You can practice this whenever you feel heaviness in your eyes and head. You can practice. So I think so. Yeah. Thank you. Over to Siddharth, sir. Yeah.
Good morning, everyone. I hope after the session you are all feeling refreshed and light. Yeah. So I cannot see your videos. So if you are working somewhere, it's okay if you can turn on your video, or you can keep your video off also. But I would like to say that participate fully in this like a short session. We are going to talk about little bit about our mind and like how these things can affect our whole system, our whole life. So firstly, I would like to thank you all the people who have joined with us, and they have extracted good amount of time for this session. Okay. So like I just want to know from your side कि अभी आपने थोड़ा बहुत ये एक्सरसाइज किया है, तो आपको कुछ चेंजेस लगे होंगे आपके सिस्टम में, आपके बॉडी में, आपके माइंड में. Yes or no? Yeah. So just by doing little bit of exercise, little bit of yoga, little bit of sukshma vyayam, adding it to our life daily can make a very big change in our life. I hope all of you know compound interest. Yes or no? Compound interest पढ़ा है हमने कहीं ना कहीं स्कूल में पढ़ा है. तो योग और मेडिटेशन एक कंपाउंड इंटरेस्ट की तरह है. or if you do it on a regular basis, it can compound the happiness, the joy, the health, the good health in your life. Are you all with me? Yes? Okay. So I'll just like to share a short story before I start. This, अगर ये एक छोटा सा मैं आपको कहानी सुनाता हूँ, and this story will tell you everything about what I'm going to talk about. Okay. So it so happened that there was a big CEO of a company, and he was like CEOs are very much occupied and very busy in their managing things, and for the growth of the company they are very much responsible. So this big CEO once went to his home. एक बार अपने घर पे गए वो. So I will use English, yeah, and little bit also will use Hindi as a medium. Okay, so this big CEO went home after a long day of work, and at his home there was a small kid, his son. So his son, how small children are, they always want to play with their daddy when they come back home, and they're always excited to meet their parents when they come home. So this small kid went to his father, the CEO, and went to his father and told him that let us all play. I want to play with you, spend some time with me. So the CEO, the father, was very busy. He had to get some of his work back home. So he was very much occupied. Yeah. So then he said, then he said, okay, if I start playing with this kid, then I will not be able to do my work. So what he thought of, he gave a jigsaw puzzle. All of you know about the jigsaw puzzle. In the childhood, we used to play with them. So he gave a big jigsaw puzzle of a world map to his kid and told him that you solve this jigsaw puzzle, and once you solve this puzzle, I will play with you. Yeah. The father thought that the kid will take around 1 hour and 1.5 hours to solve that jigsaw puzzle of a big world map. But to his amazement, the kid took the jigsaw puzzle and came back in just 5 minutes. In just 5 minutes, the kid came back and told his father, "Oh, father, I solved this puzzle. I solved this big puzzle of the world map." And his father was astonished. He thought that how come a small kid, 3 or 4 years old, can solve the whole jigsaw puzzle of a world in just 5 minutes? Even an adult cannot do that. So he asked his kid in amazement that how did you do it? How did you solve this big puzzle in just 5 minutes? The answer of the kid is very amazing, and we can all relate to this answer very much in our life. The kid answered that behind this world, behind this jigsaw puzzle of a world, there was a face of a man. There was a face of a man. There was another puzzle. So I integrated, I joined, I put together the face of the man, and the world automatically came together. Yes, the world automatically integrated. The world automatically got into its own position. So the moral of the story is, if your mind, if your body, if your intellect is integrated, everything around us will also be integrated, and very much according to what we want. Yes. And if our own mind, if our own body, if our own system, if our own hormones, if our own emotions are disintegrated, not in harmony, not working properly, there is some disharmony, then whatsoever brilliant situations are around us, we are not able to enjoy them. Am I making sense here? Yes, no. So the first thing we need to learn is how to fix our own mind. I always say in my sessions, the best kind of management is mind management. And all the managements of this world, I repeat it, I would like to quote this thing, all the managements of the world start with mind management. Before managing people, you should know how to manage our own mind. Yes, no? Otherwise, it becomes a lot of struggle. Yeah. So the first thing we need to understand is, हमको अपना खुद का मन कैसे संभाल के रखना है, हम अपने खुद के मन को कैसे सुचारू रूप से चला सकते हैं. And this, I'll just take 1 minute to explain this cycle. And this is a very important cycle, and most of the people fall into this trap of this cycle. See, in our life, we have to face lot of events. हमारी लाइफ में बहुत सारे घटनाएं घटती हैं, सिचुएशंस आती हैं, लोग आते हैं, और उनके बिहेवियर्स आते हैं. we have to encounter a lot of events, situations, circumstances, and people in our life. These events give rise to experiences, what we call experience. Like suppose you went into a marriage and the food was not good, so it created an experience for you. You are going on the road and you forgot your jacket. अभी सर्दियां शुरू हो गई, आप सड़क पे निकल गए बिना जैकेट पहने हुए. So it created an experience for you. आपको बाहर जाके सर्दी लगेगी and you feel okay, I'm feeling cold. So these experiences may be good or bad, depending upon how you take those events. Experience अच्छे भी हो सकते हैं, बुरे भी हो सकते हैं, depending upon situation या आपके मन की स्थिति कैसी है. यही experiences आपके माइंड को इफेक्ट करते हैं, आपके थॉट्स को इफेक्ट करते हैं और आपके इंटेलेक्ट को इफेक्ट करते हैं, आपकी बुद्धि को इफेक्ट करते हैं. जब ओवर अ पीरियड ऑफ टाइम ये इवेंट्स कंटिन्यू होते हैं या अलग अलग इवेंट्स आते रहते हैं आपकी लाइफ में, ये आपके एंजाइटी को इफेक्ट करने लग जाते हैं, आपको कई बार स्ट्रेस में लेके आ जाते हैं. अगर इफ यू कीप थिंकिंग अबाउट द सेम इवेंट, सेम एक्सपीरियंसेस, वही एक्सपीरियंस आपको स्ट्रेस में लेके चला जाता है, एंजाइटी में लेके चला जाता है. And these stress and anxiety then affect your impressions. They make impressions on your mind. यही impressions बन जाते हैं, आपकी मेमोरी में फिट हो जाते हैं कि हाँ उस शादी में गए थे, खाना अच्छा नहीं था, या something like this. उस time I trusted this person and this person cheated on me. So they create an impression in your mind. And when there are good impressions, it is okay. But when there are miserable experiences, they give rise to miserable impressions or sad impressions. And they ultimately affect again the events of your life. You know, when you act out of these impressions, they will give rise to same events again and again. That's why people think that it goes on round and round. ये एक सर्कल है जो चलता रहता है बार बार, because हम क्या कर रहे हैं, इवेंट्स से माइंड पे इफेक्ट आ रहा है, माइंड से हमारे स्ट्रेस पे इफेक्ट आ रहा है, स्ट्रेस से हमारे इंप्रेशंस बन रहे हैं और उन्हीं इंप्रेशंस को लेके हम वापस से नई सिचुएशंस क्रिएट कर रहे हैं अपनी लाइफ में. सो आर यू गेटिंग दिस साइकिल? सो इट इज नॉट इम्पॉसिबल टू ब्रेक दिस साइकिल, इट इज पॉसिबल टू ब्रेक दिस साइकिल. द गुड न्यूज इज दैट कि इस साइकिल को हम ब्रेक कर सकते हैं, इस साइकिल से हम बाहर निकल सकते हैं. कैसे? हमको फर्स्ट जो हमारा स्टेप था, इवेंट्स, लाइफ की सर्कमस्टेंसेस, उनको हम कंट्रोल नहीं कर सकते. दे आर लाइक व्हाट दे आर ऑलवेज बीन देयर, समटाइम्स गुड समटाइम्स बैड. बट हम क्या कर सकते हैं, उन इवेंट से हम किस तरह से इफेक्ट हो रहे हैं, दैट वी कैन चेंज एंड दैट वी आर लर्निंग इन दिस सेशन. अभी आपने जो योग किया, थोड़ा सा सूक्ष्म व्यायाम किया, वो क्या किया, उसके थ्रू हमने अपनी लाइफ को, अपने सिस्टम को एक पॉजिटिव इंप्रेशन बनाने का ट्रेनिंग दिया, एक पॉजिटिव हैबिट डेवलप करने का ट्रेनिंग दिया. एंड आई एम श्योर इस कोरोना पैंडेमिक के बाद में हम सबको एक बात तो अच्छे से समझ में आ गई है कि हेल्थ कोई ऑप्शनल सब्जेक्ट नहीं है. हेल्थ इज नॉट एन ऑप्शनल डिसिप्लिन, इट इज अ कंपल्सरी नेसेसिटी डिसिप्लिन ऑफ आवर लाइफ. डू यू एग्री विद मी? यस और नो? You know, whatever we may be experts in our, we all are experts in our domains. But one thing is common, one subject is common in all our domains, that is good, healthy lifestyle. You know, yeah. So like, you know, I saw that 1992 scam. There was a series on the Netflix, on Amazon. So he said that one subject is common, that is profit in share market. So in life, there is one subject common, that is good health. Not just health, good health I'm talking about. And when I say health, health doesn't mean absence of disease or just physical health. When I say health, I mean mental, physical and emotional well-being. आपका शारीरिक, मानसिक और भावनात्मक तौर पे क्या हम हेल्दी फील कर रहे हैं, क्या हमारे इमोशंस हेल्दी हैं. सो ये सब चीजें कैसे डेवलप होंगी? थ्रू फोकसिंग ऑन टेंडेंसीज ऑफ द माइंड, डेवलपिंग गुड हैबिट्स ऑफ द माइंड, डेवलपिंग गुड हैबिट्स ऑफ द इंटेलेक्ट, डेवलपिंग गुड हैबिट्स एट द लेवल ऑफ योर बॉडी. एंड दैट्स व्हाट वी आर लर्निंग इन दिस सेशन. या सो लाइक आई टोल्ड यू दैट ऑल दीज थिंग्स स्टार्ट फ्रॉम द माइंड. हर एक कोई भी चीज होती है आपके माइंड को इफेक्ट करती है. अगर मैं पूछूं, आप बोलते हो the food is very tasty. If I ask you what is that faculty that is feeling the taste. It is the mind. Sometimes you say, I am feeling very confident. मैं बहुत confident feel कर रहा हूँ. तो क्या confidence feel कर रहा है? आपका मन confidence feel कर रहा है. So every experience of your life affects your mind. But the thing with the mind is, you cannot handle mind at the level of mind. आप मन को मन के स्तर पे कंट्रोल नहीं कर सकते. जैसे कि फॉर एग्जाम्पल, बहुत से लोग बोलते हैं, सर हम गुस्सा कंट्रोल करना चाहते हैं लेकिन होता नहीं है. क्यों नहीं होता है? क्योंकि वो मन को ही गुस्सा आ रहा है और मन ही मन को समझा रहा है कि अरे गुस्सा नहीं करना चाहिए. Yes or no? It is so funny sometimes. Like many people say, okay, सर हम कमिटमेंट से कोई भी काम नहीं कर पाते, हमको जल्दी से बोर हो जाते हैं किसी भी काम को करने के लिए. सो बोर कौन हो रहा है? मन ही हो रहा है. और कमिटमेंट भी किसको चाहिए? मन को ही चाहिए. सो द थिंग हियर इज, you cannot handle mind at the level of mind. You need something beyond mind which can handle it, and that is breath. वो है श्वास, breathing techniques. That's why in India and now everywhere around the world, there is lot of importance being given to breath. You know, personally, I have taken many sessions, and Shreya and Parasji have taken many sessions on these breathing techniques all around the globe and in different domains. So जो breathing techniques होती है, ये हमारे मन को कैसे handle करती है? Let's have a quick look. Now just understand this thing. जब आपके मन की भावनाएं अलग होती हैं, चेंज होती हैं, तब भी आपके breath pattern भी change हो जाते हैं. When your emotions of the mind change, the breathing pattern changes along with that. Yeah, like suppose you are angry. जब गुस्सा होते हैं तो श्वास कैसी चलती है? तेज चलेगी. When you are sad or not feeling good, your breath is heavy. Heavy चलती है श्वास. And when you're very happy, you don't feel the breath. You're very relaxed and you don't even feel the breath. Yeah. So there is a correlation. There is a correlation between breath and your mind. Yeah. So you cannot handle the mind, but you can handle your breath. And that's where breathing techniques play a role. हम अपनी श्वास को कुछ हद तक कंट्रोल कर सकते हैं और उसी को ब्रीदिंग एक्सरसाइज कहा जाता है. So when you have, you know, this is also a scientific fact that you drain out 90% of the toxins through breathing. Whatever toxins are generated in your system, जितना भी गंदगी या unwanted चीजें आपके सिस्टम में जनरेट होती हैं, आप 90% श्वास के द्वारा बाहर निकालते हैं और केवल 10% जो है वो यूरिन एंड स्टूल एंड स्वेट के थ्रू बाहर निकलता है. So breath is such a detoxifier, such a big detoxifier. So if anybody has to take one big takeaway from this session, it has to be the breathing techniques or the breath and the mind connect. Are you all here with me? I cannot see you. I feel like I'm taking a YouTube video. But yeah, still, this is very important one takeaway, that श्वास और मन का कैसा कनेक्शन है. और अभी हम आपको प्रैक्टिकली करके देखेंगे हम लोग सब. We'll make you do a little bit breathing techniques so that you are able to come out of that cycle. जो साइकिल का हमने अभी बात किया था, उस साइकिल से हम लोग बाहर आ पाए. तो अभी हम प्रैक्टिकली ब्रीदिंग टेक्निक करके देखेंगे और देखेंगे कि कैसे ब्रेथ हमारे माइंड को भी रिलैक्स करती है, हमारे सिस्टम को भी प्यूरिफाई करती है, जैसे मैंने बताया टॉक्सिन्स ड्रेन आउट होते हैं. एंड यू नो, breath, see, we all can live without food, we all can live without luxuries, we all can live without our friends, but we cannot live without breath. So breath is the most beautiful asset, I would say, that we have got from the nature. And once we know how to use our breath, then everything starts falling into place. Yeah, our tendencies of the mind also start taking their own place. Okay, so I just invite Miss Shreya for the technique, and after that technique, we'll do a short meditation technique that also Shreya will guide us through. So over to Shreya ji, please guide us. Thank you, everyone.
Yeah, so we'll just sit comfortably and easily for meditation. So before that, we'll do a small practice of breathing technique, that is Bhastrika. It's also known as instant energy booster, right? So sometimes while you're working or you're traveling, you feel like the whole energy is drained, you feel dull. You can do this practice, but but when you're alone, not in front of people. Yeah. So what you have to do, sit comfortably and easily, spine erect. Now bring your hand in front of your shoulders and fist slightly closed. ढीली मुट्ठियां कंधों के सामने, and your elbows will be touching your body, right? So first we'll do the action and then we'll connect it with our breath, and then we'll practice this breathing technique, right? So whenever I will say breathe in, your hands will go up and your fist will get open. जब भी मैं आपको बोलूंगी श्वास अंदर ले, हाथ ऊपर जाएंगे और मुट्ठियां खुल जाएंगी. And whenever I'll give a count, your hands will come down and your fist will be closed. So breathe in, hand goes up, open your fist, 1, hand comes down, fist closed. और आपके knuckles आपकी screen को face करेंगे. Knuckles will face the screen, it will be like this. Yeah. So breathe in, hand goes up, open your fist, 3, in, breathe in, 4, comes down, in, 5, in, 6, and relax. Whenever I will say relax, your hands will be on your knees, open to the sky. हथेलियां घुटनों पे होंगी, आसमान की ओर खुली हुई. Whenever I will say relax. So now we'll connect it with our breath, right? So again, loose fist in front of your shoulders. While I'll say breathe in, you have to fill your lungs and breathe in. And whenever I'll give a count, you have to breathe out forcefully. Again, breathe in, hand goes up, fist open, and whenever the count is, breathe out forcefully. In, hand goes up, 3, in, 4, in, 5, in, 6. This was just a practice. So in this, you might feel ki there is something which is coming out of your nose. So that is totally fine, because I think so everyone's screen is off, so we cannot even see, and in virtual world we cannot see what is happening to the other side. Yeah, so do it with full force. जब आप श्वास लेंगे तो पूरे लंग्स को फिल करना है, जब आप श्वास बाहर छोड़ेंगे तो फोर्सफुली ब्रीथ आउट करना है, right? I think so everyone is clear. Yes, yes. So
Yes.
yeah, so now we'll do this process. Yes, Paraso, you want to say something? Yeah, so now we'll do this process, and this whole process will be done with your eyes closed, and we'll do 3 rounds. So now sit comfortably, spine erect, loose fist in front of your shoulders, elbows touching the body, eyes completely closed. Take a normal breath in and let go. One more deep breath in and breathe out completely. With full force, breathe in. हाथ ऊपर लेके जाएं, मुट्ठियां खोलें. 1, in, 2, in, 3, in, 4, in, 5, in, 6, in, 7, in, 8, in, 9, in, 10, in 11, in 12, in 13, in 14, in 15, and relax. Hands on your knees, open to the sky. Keep your eyes closed. Feel the flow of energy in the body. Let's get ready for second round. Loose fist in front of your shoulders. ढीली मुट्ठियां कंधों के सामने, कोहनियां शरीर को लगी हुई. Take a normal breath in and let go. With full force and enthusiasm. Breathe in. हाथ ऊपर लेके जाएं. 1, in, 2, in, 3, in, 4, in, 5, in, 6, in, 7, in, 8, in, 9, in, 10, in, 11, in, 12, in, 13, in, 14, in, 15, and relax. Hands on your knees, open to the sky. Keep your eyes closed. Feel the flow of energy in the body. शरीर में हो रहे शक्ति के संचार को महसूस करें. Let's get ready for final round of Bhastrika. Loose fist in front of your shoulders. Elbows touching the body. With full force and enthusiasm, breathe in. 1, in, 2, in, 3, in, 4, in, 5, in, 6, in, 7, in, 8, in, 9, in, 10, in, 11, in, 12, in, 13, in, 14, in, 15, and relax. Keep your eyes closed.
आराम से बैठ जाएं. Sit comfortably. Eyes closed. आंखें बंद रखेंगे. दोनों हथेलियां आपके घुटनों पे रखें. Hands on your knees, palms facing the sky. Back straight, पीठ को सीधा कर लें. And shoulders relax, कंधों को ढीला छोड़ दें. चेहरे पर सुंदर सी मुस्कुराहट, gentle smile on your face. Take a deep breath in and breathe out. One more deep breath in And breathing out, relax your mind. सांस छोड़ते छोड़ते अपने मन को ढीला छोड़ दें. Eyes closed. Now, become aware of your surroundings. अपना ध्यान आसपास के वातावरण पर ले जाएं. Listen all the noises around you. आसपास जो भी आवाजें आ रही है, उन सभी आवाजों को सुने. People are talking around you. आपके आसपास कोई बात कर रहा है. Accept all the sounds. जो भी आवाजें आ रही है, उन सभी आवाजों को स्वीकार कर ले. Be in harmony with the environment. बाहर जैसा भी वातावरण है, उसके साथ एक रूप हो जाएं, लयबद्ध हो जाएं. Be in harmony with the environment. Take a deep breath in and breathe out. धीरे धीरे सांस को बाहर छोड़ें. One more deep breath in. Hold the breath and breathing out. Relax your mind. Become aware of your physical body. आप अपना ध्यान अपने शरीर की तरफ ले जाएं. Your body is a beautiful gift to you by the nature or God. आपका ये शरीर जो आपको मिला है, वो भगवान और प्रकृति से मिला एक सुंदर उपहार है. Honor and respect your body. Take your attention to your right foot. अपना ध्यान अपने दाहिने पैर पर ले जाएं. Right knee, right thigh, right hip, the whole right leg. Take a deep breath in and relax your whole right leg. Take your attention to your left foot. Left knee, left thigh, left hip, the whole left leg. Relax your whole left leg. Take a deep breath in and breathing out. Relax your whole left leg. Take your attention to your genital area. stomach or navel area, chest, right shoulder, right arm. Take your attention to your left shoulder, left arm, throat, neck area. Relax your neck region, face. Take your attention to your face region. Relax your face muscles. Top of the head. अपना ध्यान आप अपने सर की चोटी पर ले जाएं. Top of the head. The whole body. Take your attention to your whole body. सर से पांव तक पूरे शरीर के प्रति सजग हो जाएं. The whole body. Take a deep breath in and breathing out. Relax your whole body. सर से पांव तक पूरे शरीर को ढीला छोड़ दे. One more deep breath in and breathe out. Become aware of your thoughts. अभी मन में जो भी विचार आ रहे हैं उसके प्रति सजग हो जाएं. Whether good thoughts or bad thoughts, let them come. Be in harmony with them. अभी मन में अच्छे विचार आ रहे हैं या बुरे विचार, जैसे भी है उसको आने दें. Do not resist your thoughts. Let them come. Be in harmony with your thoughts. Now you are in harmony with your thoughts. Become aware of your feelings. You are peace. You are joy. आप ही शांति है और आप ही आनंद है. You are peace. You are joy. Become aware of your feelings. Become aware of your thoughts. Become aware of your body. Become aware of the rhythm of your breath. सांस की लय के प्रति सजग हो जाएं. Become aware of your surroundings. Take a deep breath in and breathe out. लोका समस्ता सुखिनो भवन्तु. लोका समस्ता सुखिनो भवन्तु. लोका समस्ता सुखिनो भवन्तु। ओम शांति शांति शांति। Take a deep breath in and breathe out. और जब भी आपका मन करे अपना समय लेते हुए मुस्कुराते मुस्कुराते अपनी आंखें खोल सकते हैं। Slowly and gradually you may open your eyes. धीरे धीरे अपनी आंखें खोलें। Good. So how is the mind right now? अभी मन कैसा है? कितनों को एकदम रिलैक्स फील हो रहा है? वाह, बिल्कुल। तो मैं सबसे यही कहूंगा कि एक दिन के सेशन से कुछ नहीं होगा। एक दिन जस्ट एक, ये तो ट्रेलर था। यस, अगर आप चाहते हो कि ऐसा स्टेट ऑफ माइंड हमेशा रहे आपका, यस, आप हेल्दी रहे, यस, तो इसके लिए रेगुलर बेसिस पे हमें कुछ ना कुछ टेक्निक्स प्रैक्टिस करनी पड़ेगी। जो आज हमने सीखा है तो कुछ भी नहीं है, इससे 10,000 टाइम पावरफुल है सुदर्शन क्रिया। जिन्होंने ऑलरेडी सुदर्शन क्रिया एक्सपीरियंस की है वो अच्छे से जानते हैं कि सुदर्शन क्रिया इज अ वेरी पावरफुल राइदमिक ब्रीथिंग टेक्निक जो हम आर्ट ऑफ लिविंग के प्रोग्राम्स में सिखाते हैं। और आप सभी के लिए गुड न्यूज ये है कि टेक्यूब के अंदर ही ये प्रोग्राम एक फैकल्टी डेवलपमेंट के नाम से हम लोग करवाते हैं, जो कि टेक्यूब के नॉर्म्स के अंदर ही है, जिसमें हमें पर्सनली कोई कंट्रीब्यूशन नहीं देना पड़ता है। तो आप सभी फैकल्टीज और सपोर्टिंग स्टाफ को प्रोग्राम्स अटेंड कर सकते हैं। अगर आप इंटरेस्टेड हो तो आप हमसे कांटेक्ट कर सकते हैं। तो आपके कॉलेज में ऐसा एक 6 डेज प्रोग्राम ऑनलाइन ही हम लोग ऑर्गेनाइज कर सकते हैं। और आप जरूर से सुदर्शन क्रिया सीखें। सुदर्शन क्रिया से इम्यूनिटी इतनी ज्यादा स्ट्रांग हो जाती है कि जो लोग कोरोना पॉजिटिव भी हो गए थे, सुदर्शन क्रिया करने से उनको काफी उससे फायदा मिला, बहुत जल्दी उससे रिकवर हो गए। तो थैंक यू सो मच पीके अग्रवाल सर, थैंक यू सो मच कि आपने हमें अपॉर्चुनिटी दी कि हम सबकी लाइफ में आज थोड़ा सा कुछ कंट्रीब्यूट कर पाए। थैंक यू सो मच अग्रवाल सर, थैंक यू सो मच।
Thank you पारस कोहली सर, एंड थैंक यू ऑल द टीम मेंबर्स, एंड बहुत बहुत आपका आभार। आपने वास्तव में समय निकाल के हम सबके लिए एक बहुत ही अच्छा काम किया है। डेफिनेटली जो आपने अभी कहा है उसके बारे में हम बात करेंगे इंस्टीट्यूट पे, और वापस हम आपसे मिलते हैं सर। थैंक यू सो मच सिद्धार्थ जी, थैंक यू श्रेया जी, थैंक यू पारस जी। मैं राजस्थान तकनीकी विश्वविद्यालय की तरफ से और खुद की तरफ से पर्सनली आप सबका बहुत बहुत आभार प्रकट करता हूँ। माथुर साहब नमस्ते।
थैंक यू पारस जी,
थैंक यू माथुर सर,
थैंक यू मैडम फॉर ज्वाइनिंग अस and guiding a wonderful exercises and discussions. I hope our cooperation will continue in future also. Thank you very much.
Thank you so much. Have a nice day.
हाँ, बिल्कुल सही समय पर IIT हैदराबाद के प्रोफेसर KVL सुब्रमण्यम साहब ने ज्वाइन कर लिया था। मैं उनका स्वागत करता हूँ और मैं सर संक्षिप्त परिचय दे दूं। वैसे तो बहुत सब लोग जानते हैं देश विदेश में सर को। सर ने माइक्रोस्ट्रक्चर ऑफ कंक्रीट में और अब हाल ही में कंपोजिट सीमेंट के प्रोडक्शन और डेवलपमेंट में काफी काम किया है। IIT हैदराबाद में काफी सालों तक सर हेड ऑफ द सिविल इंजीनियरिंग डिपार्टमेंट रहे हैं और पूरे डिपार्टमेंट को एस्टेब्लिश करने में, और आप देखेंगे विश्व स्तरीय इंस्ट्रूमेंट्स को इन्होंने वहाँ एस्टेब्लिश किया। सिविल इंजीनियरिंग में एनालिटिकल इंस्ट्रूमेंट्स का बहुत ज्यादा उपयोग करने के प्रति देश में सजगता नहीं थी और उसको इन्होंने यूज करवाया। सो आई इनवाइट प्रोफेसर सुब्रमण्यम सर टू प्रेजेंट ऑन कंपोजिट सीमेंट।
Good morning, Dr. Agarwal. Good morning to all the organizers. Good morning to all the participants. We're meeting virtually by this medium, and I've been given a chance to present here on some of the work we have done on the use of, I should say, utilization of post-industrial waste materials. So I think I have been allotted 1 hour.
Yes, sir. Yes, sir. We have been somewhat late. Of course, Narayan sir session is at 11 a.m. So
Okay.
Narayan sir is already here. So he will start at 11 or 11:05. Sir.
Okay.
So it's a pleasure for. In fact, if Dr. Subramaniam takes more time of mine, also it's a pleasure listening to him. Thank you. Please take some more time of mine also.
Sure. Okay, because I had prepared an elaborate presentation. So on different aspects. So let me, since you mentioned that material characterization and the things that we are doing at IIT Hyderabad. So मैंने सोचा थोड़ा सा I'll give an introduction of this and actually stress on the importance of characterization. So that I think I would like to stress. And the other thing is for those of us who are working in cements and alternate binders and materials, particularly related to construction materials, I think we have to familiarize ourselves with the different characterization techniques. We have to also gain an appreciation for chemistry. ये अगर हम नहीं करेंगे, if we don't do these things, then I don't think we will be in a position to make any real contribution or make any innovation in this field. So with that, let me share my screen. Okay, I'm currently sharing my screen. I'll go into a video mute mode. So. Okay, to save on the bandwidth. So I'm presuming everybody can see my screen. Please do let me know.
Yes,
if,
sir. Yes,
yeah,
sir.
Thank you.
It's visible, sir.
Thank you. Right. So now I'm in the presentation mode. So the topic that was given to me by Agarwalji was to talk on production of low energy Portland composite cements from post-industrial waste. So first thing, a little bit of background of what why is it that we are chasing these cements and where is it? What is the scenario for these materials? First thing, of course, is the mothership or the parent from which we all basically start our search is concrete, and we know that it is one of the most utilized material on this planet. Basically, if you look at concrete, it's everywhere. It's basically the usage of this material is nearly 2 tons per year for every human being on this planet. So it is second only to water. So this is a material that we have to produce. We have to continue to produce in order to sustain our growth of infrastructure. Now, oftentimes when we talk about cement and concrete, these two terms are used in an interchangeable manner. So even in civil engineering literature, it's not unusual to see cement and concrete being used interchangeably. But we have to realize that cement is, of course, only a component of concrete. We have aggregate also that come into play. And of course, now even admixtures make up a good chunk of concrete. And if you actually look at it, cement only makes up about 7 to 15% of the total mass of concrete. But it is the most key ingredient because this is that one ingredient that is responsible for strength. It is responsible for all the durability properties of concrete. So a little perspective on cement. We are not new on the scene. We think we've invented the world, but we have not. Romans had quite an advanced technology of cement. To this day, we don't know if it was done in a scientific manner or if it was done by trial and error or if they basically stumbled upon it. But the Roman concrete, as we are discovering now, as we are starting to look into the historic structures built by the Romans, basically has a very similar composition to what we are using in modern concrete. They were using cements, and they were using hydraulic cements, which were basically a cement which would react in water, set, and basically give the properties. And what I'm showing you here is a photograph of the Pantheon, which is a structure that was built almost 2,000 years ago and made of concrete. There are some wonderful things about this structure, which includes the use of admixtures. They were using admixtures for increasing the workability of concrete. They had used admixtures for improving the freeze-thaw resistance of concrete. And of course, the products they were using were of biological origin. That is, they were basically using things that are derived and more organic. But the intent was clear. So they basically had mastered the technology, and almost for 2000 years, nothing much happened. And in fact, if anything, we slipped backwards in terms of cement and concrete. And the other thing that we keep coming across in terms of utilization of waste materials is the Roman concrete, of course, had well, they used aggregate, and they also had mortars. They had a binder, and they also came up with this term pozzolana, which of course, has become very common in usage today. They found that this volcanic ash that they found off of the island of Sicily, when they mixed it with lime, and they even had worked out the proportions of this. They mixed lime and pozzolana in a proportion 1:3, and they found that that made a very good binder. And today, as we are rediscovering the chemistry, we find that this is actually a good proportion to use. And now, of course, with the knowledge of chemistry, we are doing all these things, but somehow they either figured it out or they had some advanced knowledge that we are still yet to discover. And I'm just showing you a photograph of a structure. This is actually an aqueduct, which is still in use today. This was built 2000 years ago. Of course, this aqueduct is made of masonry, but the binder they used was basically a cementitious binder. And this has lasted 2000 years. Now, a little bit of background on other mortars that have been in use. One of them is, of course, lime mortar. It has been traditionally used even in India. Practically everything that was built up to almost 100 years ago was made with lime mortar. And it's a very simple chemistry here, where you take limestone, which is basically calcium carbonate, you heat it to 1000 degrees, essentially calcine it. That breaks up into calcium oxide, which is what we call chunna or lime powder, and you mix it with water. That turns into a paste, and that paste basically is calcium hydroxide. And then when that reacts with carbon dioxide in the atmosphere, it gives off calcium carbonate. So now basically you start with a rock, you end up with a rock. So what happens, you basically apply this lime between bricks or stones, and as it hardens and as it forms calcium carbonate, it basically binds these material together. Now, the interesting thing about this reaction is, it is carbon neutral. So you basically start with calcium carbonate, you release carbon dioxide into the atmosphere. But when the reaction is complete, you basically bind all the carbon dioxide back. So basically it is carbon neutral. The only carbon footprint of this material would be the energy that basically the carbon dioxide that will be produced in heating the material. So that is the only carbon footprint that one would have to account for. And this material has been used extensively in structures that have lasted forever, including all of our historic monuments that we see in India, the Great Wall of China, which has been in existence for 2000 years. So it's a very good material. And the interesting thing about this is that basically it gains strength as we go along. The reaction of calcium hydroxide converting to calcium carbonate is a slow reaction, and it takes a long time to complete. So even as we speak, even the 2000-year-old structures are still gaining strength because this conversion process is still on. Now, the reason I talk about this history is, if you look at the thread that is coming through here, is that people were predominantly using calcium-based materials. So if you look at, if I just go to the previous slide, if you look at the pozzolana that the Romans were using, now we are finding that it had some calcium, but more importantly, it had silica and alumina in it. And the silica is something that we'll see later plays a very important role. And they, of course, mixed it with lime. So lime is the calcium source. So calcium and silica seem to be two things that are important in understanding cement chemistry or cements, and calcium again. So if you look at lime mortar, that's again a calcium product. So the two things that we have to pay attention to is calcium and silica. These are two important elements that we need to pay attention to when we're talking about cement. Now, if you look at the historic development of cement, of course, we look back to the Roman Pantheon, which is 126 AD, and some other developments that have happened. But the first systematic procedure for making our normal cement was patented in 1834 by Joseph Aspidin. Then, of course, subsequent developments happened while we were able to make cement and concrete. By the time the design methods came about, that was in the early 1900s, and then of course now we are able to take it further with the use of pre-stressed concrete. So these are all the developments that have happened with the use of the material. Now let me talk a little bit about cement manufacture. We need to understand the chemistry of this material. If you look at modern cements today, Primarily, they are calcium oxide and silica. These are the two prime ingredients in cement. Calcium oxide typically makes up about 60 to 70%. Silicon oxide, and I'll just loosely call it silicon oxide. We'll see later that we need to understand really what this silicon oxide is. It makes up about anywhere from 20 to 25%. And so these are the two primary ingredients that make up modern cement. So the calcium and the silica keep coming up again and again. And even in modern day cements, it's calcium and silica, and primary components are calcium silicates in cement. So basically, cement chemistry is all about understanding calcium silicate chemistry. Now, as I had mentioned before, in the manufacture of cement, therefore, if I have to produce a calcium silicate, I need sources of material that can give me calcium and silica. So usually, and this has not changed. So if you look at the limestone, it's still the source that we use for the source of calcium. This is similar to what was used in the lime mortar for 2000 years. And silica is we use sources like clay, which basically brings in the silica. So these are the two, or these are the raw materials which basically bring in the calcium and the silica that are needed to make the cement, so that we can produce a calcium silicate material. Now, of course, clay and limestone are both naturally occurring materials. Clay in particular varies a lot in composition. We know that different types of clays depending on the mineralogy of the clay, and therefore oftentimes when we use clay in the manufacture of cement, we cannot avoid bringing in alumina, Al2O3, from the clay, and also iron. Clay also contains some iron, and that brings in that Fe component, or the iron component, into the cement. The manufacture itself again requires heat and energy. So again, this is a similar thing to what was done with the lime mortar. You actually have to free up the calcium from the limestone. So basically, the cement manufacture takes place in these rotary kilns, and these are massive drums. I'll show you photographs of these. And the raw material is basically limestone and clay, and that is added into this hopper, and the material basically comes into this kiln. And I'll show you what is happening in the kiln in the next slide. But if you look at limestone, basically, and I heat it up, it gets calcined. So that process is very similar to what we did with the lime mortar. It breaks up into calcium oxide. So I have my calcium, which is the ingredient that I need for making cement. And then I also add clay as my other raw material, and the clay brings in the silica element, the alumina, and the iron element. So these are the three elements that come about, or the three primary elements that come about from the clay. Now, as I heat the two of them, the calcium oxide and the clay, the calcium fuses with the silica, and then I get the calcium silicate. And of course, because I have also alumina and iron, I also get the calcium aluminate and the calcium aluminoferrite phases. These are what we call as our Bogues compounds that we read in cement chemistry. And what comes out of this then is what we call clinker, which is then ground with gypsum to produce cement. Now, if you look at this process here, the carbon footprint of this material is associated with the fossil fuel that I burn. I have to burn something to produce a high temperature, because I need temperatures on the range of 1500 degrees Celsius to produce this fusion between calcium and silica, or calcium and alumina. So to produce that, I need to burn fossil fuel. That basically gives off carbon dioxide, because most of our fossil fuels, or what I burn to produce energy, are carbon-based forms, whether it is in the form of diesel, petrol, or in the form of natural gas, or in the form of coal. They're all carbon-based, and when you burn them, you produce carbon dioxide. And the calcium carbonate, when it decomposes, of course, gives off carbon dioxide. So these are the two sources of carbon dioxide emissions coming from cement. Now, what happens in the manufacture of cement? So this is basically a schematic of the cement kiln. So here we have basically the top end of this, where I'm showing the raw feed, is where the raw feed enters into the material. Raw feed consisting of limestone and clay. This enters into the kiln, and at the other end of the kiln, which is this sloping cylinder, is where we have a source of heat. It's basically usually an open flame, and that is extremely hot. So if you look at the bottom here, I have a temperature chart. What enters the kiln at the raw feed is hot in itself. It is 450 degrees Celsius there. And at the exit stage, or basically where I have the heat source, the temperature can go as high as 1600 degrees Celsius. So it's a very, very hot drum. And this drum rotates. So it's basically rotating. So as the raw feed is dropped into the drum, and as the drum is rotating slowly, the charge basically starts moving forward. And as it starts moving forward, the temperature in the drum is increasing as we go towards the open flame, or towards the bottom end of the drum. So as the charge is moving forward, it is being exposed to a higher and higher temperature. So what happens initially? Whatever free water was available in the system, that escapes. Then I have the clay decomposition. The clay decomposes into its constituent ingredients. So it basically decomposes, and I get my silica from the clay, I get the alumina from the clay, I get the iron oxide from the clay. So these start decomposing. So it decomposes it into its component oxides or constituent oxides. Then the limestone decomposes, and I get calcium oxide. And then as the charge starts moving forward, the calcium oxide and the silica start fusing. And basically at around between 12 and 1350 degrees Celsius, I form the C2S, which is dicalcium silicate. And the tricalcium silicate is formed at a much higher temperature, close to about 1450 degrees Celsius. So basically I get these primary silicates, which are C2S and C3S, that form as the charge is moving forward, moving through this drum, and eventually the clinker is discharged at the opposite end of the drum. So this is what a cement kiln looks like. This is a rotary kiln, and now the efficiency of the kiln has been maximized. If you look at the production of cement, most of the kilns that are being operated now operate at a very high level of efficiency in terms of energy utilization, in terms of material consumption, etc. These have been optimized to the limit. But you can see that it's a very large drum. It's basically a drum that can rotate. You can see the circular bearings here. It's a sloping drum. So the bottom end of it, where you see the blue shed, is where you have the burner or the high temperature to end. The top end is where the material is fed into the drum. So now one of the ways where some of the waste material is being disposed of is happening right in cement manufacture itself. And I wanted to mention that now, because we need a source of heat, a lot of waste materials are being used in incineration, or basically these are being incinerated to produce the high temperature. So in fact, in the photograph, if you see on the left hand side, you can see tires being loaded up and they're being taken into the incinerator. And rubber has a very high calorific value, and it's very difficult to dispose of these tires, used tires. So they're being used to produce energy. Similarly, biological and hazardous waste is also being used in incineration to produce the temperature. So in the production of cement itself, a lot of this hazardous and waste material disposal is already happening. And on the right hand side, you see a photograph. It's an infrared photograph which shows the temperature of the kiln. One cannot get an idea of the temperature unless one takes an IR image, and you can see that it gets really hot inside the kiln. Now after the kiln, what comes out is a clinker, and you see the clinker is basically in the form of these nodules. They're basically these grayish stone-like material, and that is then ground in a ball mill to produce a very fine material, which we call as cement, this grayish powder. And of course, in the clinkering stage, in the grinding stage, is where we add gypsum and to produce cement. And what comes out as cement is this grayish powder, the ordinary Portland cement, as we call it. Has an average particle diameter of anywhere from 10 to about 20 microns, or 10 to 20 micrometers. It has a very high surface area. So now there's of course a whole science into the grinding process, also achieving of the sizes and the role of particle size in the reaction of the cement. Now just a quick touch up on the embodied energy. If you look at the energy that is used to producing cement, how much energy do I have to expend or spend in order to produce cement, and you compare it with other materials, actually OPC doesn't look so bad, because if you compare it with aluminum, which is probably has the highest embodied energy, because the decimerization process that's used to produce aluminum is very, very energy intensive. So that has a very high thermal energy requirement. Even steel is high. the OPC that we talk about is actually not so bad. It's actually, while it is an energy intensive material, it is not as bad compared to the other material. And that's one of those things that one has to think about when one talks about the sustainability of this material, because with all said and done, if you look at it in comparison with the other construction materials, it has probably the lowest the embodied energy compared to the other materials. But when you look at the cement scenario for India, now here's the picture that shows the past, present, and the future. So if you look at this is the production of cement as has happened in the past, what is currently happening, and what is projected in the future. The y-axis is the cement production in gigatons. And if you look at it, the red indicates China. And China has been the largest producer of cement. And rightfully so, because they have developed their infrastructure from scratch. And they basically, if you look at it from 1990, they've basically literally become from an underdeveloped country to one of the developed countries. And that has happened because they've developed their infrastructure. And that came at the cost of cement. Now, but if you look at the blue there, that is India. And India right now is the second largest producer of cement. And if you project forward to 2050, will likely be the largest producer of cement. And that is a projection based on our requirement of cement for infrastructure. As we are planning to grow our infrastructure, we'll need a lot of cement. And so that means we have to be able to produce the kind of cement to sustain the growth of our infrastructure. Now, what are the challenges with the cement production? The challenges with cement production and the anticipated requirement of 750 million tons per annum in 2050, that is the projected requirement of cement. If one is to look at that, our current available reserves of limestone are expected to last only about 35 to 40 years. And this is the grade A limestone. This is the best quality limestone that is currently used in making cement. That's only going to last us 35, 40 years, which means we have to look for alternatives. So we have to look at using, reducing the amount of clinker in cement, because remember, clinker is the one that basically comes from the use of these raw materials. We also have to, although the energy requirement of cement is less compared to the other construction materials, but if you look at the large volume in which cement is required, we have to address the energy issue. We have to look at energy and consuming less energy in making cement, and the carbon footprint. It is somehow, it is the second largest or the third largest anthropogenic source of carbon dioxide. We have to address this issue. So to make any improvements, first we have to go back to the basics. So let's look at cement hydration and the cement chemistry. And we know that the two primary compounds of cement which are responsible for most of the properties in cement are the calcium silicates, the tricalcium silicate and the dicalcium silicate. And these react with water in this reaction which we call hydration to give the calcium silicate hydrate. And of course, a lot of lime or calcium hydroxide is released in the process. Now, this is a very simplistic representation of the chemical reaction. To this date, we don't know the exact stoichiometry of calcium silicate hydrate. It's very variable. And it basically changes depending on different conditions like temperature. It also varies within the cement paste. It will vary depending upon the location at which you sample the material. So the CSH is not a fixed material. And usually when we give this composition, it is given in an average sense. So whatever you see in the chemical reaction written here, it is in an average sense. Now, we know that the hydration of cement is an exothermic reaction. Basically, it gives off heat. And we know that when I mix cement and water, it is basically like a paste. It starts out like a fluid. When it goes through this acceleration stage in the when I measure the isothermal heat release, it basically transforms into a solid, and the solid continues to gain strength. And then if you look at the microstructure of cement, if I put cement in water, this is a representation of that hydration process. Initially, I have cement grains sitting in water, which I've idealized as these circles or spheres sitting in water. With time, the cement is consumed, and what I end up with is a porous network, which basically is this porous network of water-filled tubes. These water-filled tubes are on the size of microns and even smaller. So the water-filled tubes are on the size of, in fact, they go down in size up to a few nanometers and in fractions of nanometers. So you get these small water-filled capillaries which go from nanometers up to micrometers. And with time, what happens is that as more and more cement reacts, water is consumed, and the capillary pore space starts decreasing. So the amount of the diameter of the pores, the volume that is available with water starts shrinking. Now, just to show you the complexity of this material, once it hydrates, if you look at it under a SEM, a scanning electron microscope, it is very confusing. So this is what typically awaits you. The calcium silicate hydrate itself is basically an amorphous material. It does not have a defined structure. You can see that it looks like several plates that have been loosely assembled. You can see the gaps between the plates, which is where the water resides. And to give you an idea of scale, the gap that you see here between the plates will be on the order of fractions of microns. If I actually zoom further, I may see these needle-like structures, which are basically the calcium aluminate or sulfur aluminates that have formed in the system, which we call as ettringite, and also calcium hydroxide, which is one of the byproducts of hydration reaction, forms these hexagonal crystals, because calcium hydroxide is a crystalline material. And basically, if you look at a cement grain, you see these reaction products that have formed around it. The whitish, bright whitish thing is the cement grain. You see the reaction product that has formed around it. The black in this SEM image is water. And basically what has happened is that the reaction product basically forms around the cement grain. And this reaction product is primarily calcium silicate hydrate. If I actually look at the calcium silicate hydrate, and if I sample the calcium silicate hydrate close to the cement grain, it will have a certain composition. If I sample the calcium silicate hydrate away from the cement grain, it will have a different composition. And also the way it is packed also varies. And this has enormous implications on the final strength, the final properties of the cement, of the hydrated cement, and also of the concrete. So a quick touch up on supplementary cementitious materials. Now, we need to understand that because we are trying to reduce our requirement of cement, we started exploring supplementary cementitious materials, which basically are primarily derived from post-industrial waste. And the supplementary cementitious materials most commonly used today are, we have fly ash, slag, then of course silica fume, and these are all waste materials. Now, what is fly ash itself? I'll cover this in a little bit more detail in the next few slides. It's basically what we get when we burn coal. It's that the ash that is left behind. Of course, this is the ash that is collected from the stack, or what is coming out of the chimney. It's carried by the flue gas. It's in the form of fine dust, and it's collected using electrostatic precipitators. And the way we use these supplementary cementitious materials is basically in a cement system. So I have my cement reaction between the calcium silicates and water, which leaves a lot of lime. So what we do is we basically look at these supplementary cementitious materials, which are primarily sources of silica. Most of the materials that we have, whether it is slag, fly ash, or metakaolin, or silica fume, all of these are rich in silica. So basically, these bring in the S element in the reaction. So now, because the cement hydration leaves CH, which is calcium hydroxide, if I bring in a source of S silica in the form of either fly ash or slag, basically that would consume this CH and give me additional CSH. And this is what we call our pozzolanic reaction. So basically, again, it goes back to having a system which has calcium and silica, and we are bringing in additional silica from these materials. And fly ash, basically, if you look at the oxide composition of it, depending on the clay that is burnt to make the fly ash, basically contains a variable amount of silica, SiO2. That is the primary ingredient that is used when, or what we count for when we are looking to replace cement with this material. Now, slag is another supplementary cementitious material that is made from the waste. Is basically the gunk that floats on top of the molten iron. That material is basically at a very high temperature of 2700 degrees Fahrenheit, about 1500 degrees Celsius, and that is cooled or quenched very quickly, and to give a glass-like material, and that is then ground to a fine size to produce this ground granulated blast furnace slag, which we use as a replacement. Again, this is very rich in silica, and so it's primarily a source of silica. Then we have silica fume, which is basically a byproduct of reduction of high quality or high purity quartz in an electric furnace. which is used in the high technology manufacture of silicon or silica chips. Same thing, because it is made in the manufacture of silica chips. It is very rich in silicon or silica, and it is again used as a supplementary cementitious material. Metakaolin comes from calcining clay, and as we already know from our understanding of cement production, clay contains silica. So when I calcine it, I'm basically creating a source of silica in the system. And again, it is used as a replacement. It can also be used as a cement replacement. And the whole point is that the calcium hydroxide that is produced from the cement hydration is then used up by the silica that is coming from these materials to form additional calcium silicate hydrate. So that is the whole principle of this utilization. And using this, then we have been able to basically replace the clinker content in our cement with this post-industrial waste. And remember that fly ash and slag and silica fume, these are all waste materials produced by other industry. Therefore, they are post-industrial waste materials. We've been able to find uses for these material in cement, primarily as a clinker replacement. So I'm able to replace clinker with this material. But I want to, at this point, develop an understanding of forms of silica. And this becomes very important in order for us to understand how effectively can we replace this cement with these materials. Because if you look at it, we are primarily trying to replace the silica component, because these materials are bringing in silica. And we should be aware of what forms does silica take. Now, if you look at silica, Si, as we, or silicon as we look at it, it exists in oxide forms, and we are aware of different forms of silicon oxide. And one of the forms is quartz. Quartz is nothing but sand. It is our natural sand. And quartz is one of the most inert materials known to man. It does not react. So, but at the same time, silica is also present in cement. It is also present in the supplementary cementitious materials. And somehow we know that this silica is able to enter into the reaction, which means that it is not inert. It is in a reactive form. So we have to learn to distinguish between the oxide forms of silica, and that basically takes us into silicon chemistry and silicon oxide forms. And this basically is quite complex. The silicon chemistry is actually quite complex. The way it silicon combines with oxygen, it exists in different forms, as I'm showing on this table on the right hand side, and one has to develop an appreciation for these different forms. But one should be aware that there are inert forms of silica that are present, like quartz, and if that is present, then basically I cannot use it in any chemical reaction. So that's the reason why we don't use sand typically in as a replacement of cement, because while sand is rich in silica or sand is rich in silicon, the silicon exists in an oxide form, where basically it is coordinated, or basically it is combined with 4 oxygen atoms, and in a very stable form, in a very stable crystalline form. Whereas when the silicon is combined with 3 or lesser number of oxygens, it exists in an amorphous form. It forms a network, which is shown here. And that that form of silica is, or that form of silicon is in a reactive form. That means it can actually enter into a chemical reaction. Now, I'll illustrate this with fly ash. And I know you've had a lecture yesterday given by Dr. Bhagat Singh, where he probably would have talked about fly ash in detail. I just wanted to touch upon, with fly ash, illustrate the different forms of silicon that exist, and we should learn to distinguish the reactive form of silicon. So if you look at fly ash, basically, I just wanted to show you that quartz, if you look at it under a scanning electron microscope, would have this nice crystalline form. It is silicon. So if you look at it, it's basically silicon oxide. That's what it is, but it is an inert form. But if you look at this aluminosilicate glass, and which is shown in the form of these nice spheres, this also contains silicon. But basically, this is the form of silicon. It is in a reactive form. Now, Vijay, I just want to show you what we did with characterization of fly ash. So we collected fly ash from different sources across India, and we did an oxide analysis. So oxide analysis is done by a technique known as XRF, which is X-ray fluorescence spectroscopy, which basically indicates the oxides that are present in any material. And when you look at the oxides that are present, you find that across all these fly ashes, the silicon oxide, SiO2, and the alumina, Al2O3, these are almost identical. There's very little difference between these. And there's very low lime content in our fly ashes. So basically, if you look at the primary oxides in these fly ashes, it's basically the silicon, the aluminum, and the iron oxide in fly ash make up about 70% of the fly ash. But if you remember, if you look at silicon, we had mentioned that it exists in reactive and non-reactive forms. So to identify the reactive and the non-reactive forms, we have to resort to X-ray diffraction spectroscopy. And so if you do XRD, which is X-ray diffraction spectroscopy, one can learn to distinguish between the amorphous and the crystalline materials. If you look at an XRD signature for a raw fly ash, it basically would have all these peaks that show up. And each of these peak is produced by one, or the peaks are produced by crystalline materials that are present in the fly ash. So I can basically break up this into the XRD signature of the fly ash into two parts. One is this peaks, and the second is this background or this hump that you see here, this broad hump. That broad hump is basically the amorphous portion, because when you have amorphous material, X-ray diffraction does not produce well-defined peaks. It gives a very broad, diffuse hump. So now the reason for doing this will become clear in the next slide, is when we actually start looking at the crystalline forms of the silicon. The crystalline form is primarily quartz, and I'm not interested in quartz because it is a non-reactive form. So basically, in those peaks that I showed in the previous XRD signature, those peaks contain information about the quartz in the material, and we can basically separate out how much quartz is present. And the remaining part, which is the if I go up here, the broad hump that you see in the XRD signature is basically the glassy form. This is where silicon is present in a form which is reactive. So I have to learn to distinguish or separate out the amorphous form from the crystalline forms, and that is what we did here. And for the same fly ashes now, what I'm showing in these two graphs, and if you focus on the graph on the left-hand side, you will see the total silicon oxide, SiO2, that is present, the total silica present in the material. The blue lines show the total SiO2 present in the fly ash. The green lines show the SiO2 that is present in the reactive form. What is the difference? The difference is basically the SiO2 that is present in the non-reactive form of quartz, and that basically doesn't enter into the reaction. It is that green bar, or the green bars are the form of silica that enter into reaction. So if I take some fly ash or any supplementary cementitious material, I need to identify the amount of silica that is present in this reactive form. Then I can basically start looking at cement replacement in an efficient manner. So basically, just to reiterate, I just wanted to emphasize here that material characterization is very important. If you give me any material, and if I want to use it in cement chemistry, I have to look at the primary ingredients in terms of its oxides. Now, when it comes to primary ingredients, I'm primarily interested in calcium. So I'm interested in calcium because it's calcium silicate chemistry. And I'm interested in the silica. And I need to identify, though, the form of silica. I'm interested in the reactive form of silica, which can then be used to form calcium silicate hydrate. And that is the strength-giving material of cement. So now, just to quickly show you how we optimize the use of this fly ash, which is a post-industrial waste material, in cement. So how effectively can I utilize this material? Now, if you remember the replacement strategy, and if you look at ordinary Portland cement, so if you look at it on the left-hand side, the table on the left, you know ordinary Portland cement is primarily calcium oxide, alumina, and silica. And primarily it is calcium and silica that we are interested in. And when I bring in fly ash or any other supplementary cementitious material, it basically comes with silica. It may contain some calcium oxide, and it may also contain some alumina. But primarily, we are looking to replace silica in the cement with the silica that is coming from the fly ash. Now, in order for me to do that, then, for me to do an effective replacement, it is the reactive silica that is present in the fly ash that I can use to replace the cement. So if I add, let's say, 1 kilogram of fly ash, only a small percentage of that will be available in the reactive silica form. So only that much percentage is an effective replacement of cement. And that is what we need to figure out. So basically, when I put or add fly ash into cement, or when I'm replacing cement with fly ash, I basically may gain some silica into the system because fly ash is bringing in silica, but of course I lose the calcium component, because as I remove cement, cement is primarily calcium silicates or calcium aluminate, so I lose this calcium component, and the calcium that is coming from fly ash is very small, so therefore the calcium content decreases. And basically, I lose out on the calcium silicate hydrate that the cement that I'm replacing would produce. So basically, net, I have to figure out what is the total gain and what is the total loss. And for actually characterizing that, what we have done is to develop, look at these numbers. And suppose I look at 20% replacement, and I'm giving you a numerical example. If you look at cement, which is shown on the table on the top, basically, cement contains 3% alumina, 15.76% silica, and about 71% of calcium. And when I replace, let's say, 20% of the cement with fly ash, and I'm only showing the reactive components of fly ash, basically the fly ash that we had done in this case, replacement, gave 21% reactive silica. So it had 21% by its mass reactive silica. It had 11% alumina reactive form and only 1.92% calcium. So basically, if I replace now cement with fly ash, I increase the alumina content, I increase the total silica content in the system, but there's a reduction in the calcium oxide content. So this is the trade-off. And when you actually look at an M35 mix, which was basically done for a 42 megapascal compressive strength, at 20% replacement, we were able to achieve about 59 megapascal strength, because net we were able to produce more calcium silicate hydrate in the system. Now, we developed an efficiency factor for this, for optimizing the replacement, which basically is a metric for replacement. The efficiency factor itself is based on trying to an understanding of the Arrhenius type reaction. But just to give you the way the efficiency factor, the C efficiency that I've shown here works, is that to develop an optimal replacement, the idea would be to achieve the same strength as what I would without using the fly ash. And we just saw in the previous example that if I do only 20% replacement of cement with fly ash, then basically I can actually improve the strength, because what happened in that system is, yes, while I lost some calcium, which went with the cement, but I brought in more silicon. And remember that in a cement system, it's a calcium rich system because a lot of calcium hydroxide is produced. So net, I was able to produce more calcium silicate hydrate in the system, which gave higher strength. So now this efficiency factor that we've developed, basically the point would be to achieve an efficiency factor of 1. And if I achieve an efficiency factor of 1, then basically I have the optimal replacement level of this material, which is based on the reactive components that the this particular fly ash is bringing into the system. So the maximum cement substitution with any of these post-industrial waste materials would basically be based on achieving an efficiency factor of 1, which would basically give me same strength and performance as what I get with using pure cement. So now using this metric for typical fly ashes in India, we worked out that the typical replacement levels would be anywhere from 30 to 40%. And remember, the code anyway puts a cap on the replacement at about 35%. So this number seems quite reasonable using or looking at our data. Now, I just wanted to show you in this graph the efficiency factor when you start increasing the replacement level. So basically, when we started increasing the replacement level of fly ash at 70%, you see the efficiency drops off, and the maximum efficiency that we were able to get in the system was about 70%. So that means that you can only maximum achieve 70% of the strength using a pure cement system. So just to show you that other supplementary cementitious material, typically we have this representation in what is known as a ternary diagram. In a ternary diagram, you basically have calcium oxide, alumina, and silica. And basically based on the composition of these materials, they will basically come as a point on this in this ternary diagram. And if you look at it, our Portland cement, which is this grayish circle PC, basically is sitting in the calcium-rich corner. The fly ash, which is the maroon circle, is sitting in the silica-rich corner. The Silica fume is pure silica. So that is sitting in the corner, which is basically marked as SiO2. Slag is quite close to PC, which means basically slag would be mimicking cement, and therefore I can look at a higher level of replacement of cement with slag, and that's the reason why when we are replacing cement with slag, we are able to go up to 70% replacement without sacrificing strength. Similarly, we can work out for all the other materials, and remember, most of these are post-industrial waste materials, except metakaolin, which is basically a manufactured material, but most of the other materials are post-industrial waste. They're waste materials derived from other industry. So with these blended cements, then we basically have replacement of cement with blast furnace slag and or fly ash, and basically we are relying on the pozzolanic activity. And these blended cements are now commercially available. They have several advantages, which include lower heat of hydration, increased durability, increased strength. These are all now known and have been established. And this is a typical replacement chart with fly ash, where we are stuck at 35%. And of course, with slag, we can go up to 70%. So, but what about Portland composite cement? Now, Portland composite cement is produced by intergrinding or blending clinker with other cementitious materials. Now, where it is different than pozzolanic cements is that we intergrind this. We intergrind slag or clinker with this, and we use multiple sources of silica or multiple materials in this intergrinding process. And the composition or the replacement of clinker can go from 30 to 80%. And basically, we can use different supplementary cementitious materials like fly ash, slag, limestone, and silica fume, and combinations of these. So we're not restricted to using only one material. And now there's even a BIS standard available for composite cements. Now, what I would like to talk in the last unit is production of this Portland composite cement. I want to basically talk about this experiment that we took up, where we wanted to make cement using only waste materials. So we wanted to source waste materials, of course, understanding the chemistry, and be able to produce a cement which basically gives us the same calcium silicate hydrate chemistry. That was our objective. So now we even set up a vertical kiln. So in my first few slides, I had shown a rotary kiln. Now, a rotary kiln is basically very expensive to set up. So to demonstrate a pilot scale production, we set up a vertical kiln, which is actually simpler to set up. It is not very efficient, and that's the reason why it's not used by the cement industry. But to prove the production process, one can use a vertical kiln. Now, what does a kiln do? A kiln basically is nothing but a large tube, which allows me to develop this gradation in temperature. And that's what this vertical kiln did. Is basically at the bottom end, you have the high temperature heat source. At the top end is where you introduce the charged material. Charged material, remember, has to have a source of calcium. It has to have a source of silica. The material has to move slowly through the drum and basically be slowly subjected to a higher and higher temperature. And it has to be subjected to a temperature up to about 1500 degrees Celsius, the material that is passing through the kiln. Now, all of those objectives are achieved in this vertical kiln, where basically at the bottom end, the temperature was as high as 1500 degrees Celsius. At the top end, we were basically allowing or sourcing or introducing the raw material. And the material slowly moved through the drum, because as we emptied out the clinker that was forming out, the material would slowly move in. And we could slowly move the entire material through the vertical kiln so that it went through this slow process of cooking, or which allowed the calcium to separate out from the raw material, the silica to separate out from the raw material, the alumina to separate out from the raw material. And then the calcium has to fuse with the silica to produce these calcium silicates. So that process was enabled in this vertical kiln. The source materials that we used, remember I had said that we were planning to produce this cement from 100% waste. And what we used as our raw materials were lime sludge, clay, and sponge iron. Now, lime sludge is basically a waste which is produced from paper and pulp industry. And we produce almost 4.5 million tons of this lime sludge every year. Paper industry produces most of it. And basically every ton of paper that we produce results in almost 600 kilograms of lime sludge. So, but by the name itself, we know that this would probably be a source of lime. Then we had to use clay because we needed some source of silica, the Si. So for that, we used low quality clay. Now, this is basically not the good quality clay that would go into the agricultural soil, but this was basically mine overburden. This is not suitable for agriculture. This is something that lies on top of mines and is used for backfilling. So it is low quality clay that was sourced. And we use sponge iron. Basically, the reason for using sponge iron is it's a waste material that people are not able to utilize. It, of course, brings in iron, and we know that cement, OPC, ordinary Portland cement, contains some iron in it. But the reason for using this is because sponge iron contains a lot of unburnt coal and unburnt carbon, which basically is present in it. So we were looking to extract heat from this, and basically that unburnt carbon could be used as a source of heat, and thereby minimizing the requirement of the coal that was required to produce the high temperature. So this was the reason for using sponge iron in the production. Now, before we start making cement, we first have to understand the raw materials and look at what each of these materials is bringing in as a source. So if I look at lime sludge, look at these three columns. The oxides of these three are given in the first column. If you look at SiO2, which is the silica, clay is rich in silica. It has 43.6% silica, and sponge iron also contains silica. So basically, I can use these as my sources of silica. And if you look at lime, which is the other key ingredient, most of it comes from lime sludge. So that is good news. Clay also contains some lime. So basically, my two primary ingredients that I'm after are being supplied by these three materials. And then if you look at the loss on ignition, which is basically the heat loss when I burn it to 1000 degrees, it is very high for sponge iron because of all the unburnt carbon that is present there. That means if I put sponge iron with my source material, as it is moving through the kiln, it will burn and produce heat. And that basically can be used to reduce the demand on the fossil fuel for the temperature that I need in my kiln. So now let's look at these materials individually to make sure that they are present in the reactive forms. So if I look at the XRD, X-ray diffraction signature of my lime sludge, most of it is present in the form of calcite. If you see the graph, the spikes which are shown in the maroon, that says that most of my lime sludge is available in the form of calcite. Calcite is nothing but calcium carbonate, which is actually excellent because this is exactly the source that we use for making cement in the form of limestone rock. So that calcite is coming from this lime sludge. The other material is clay. So we did the X-ray diffraction of clay, and we found that clay, while it contains silica, clay contains silica in a lot of it in the form of quartz. And if you remember, quartz is a very inert form of silica. So this is not of use to me, but it can't be helped because this is low-grade clay which contains silica in the form of quartz, which will be non-reactive. So I have to now to see what is the silica that this clay brings in the reactive form. And that is given by this line shown here at the very bottom, which is shown as the glassy portion. This is that silica that is available in the glassy portion. Just similar to what we had seen in fly ash, the glassy part is where the silica is present in the reactive form. There's something else that I wanted to mention, and that is the calcium in this clay is present in the form of calcite, which is calcium carbonate, which I can readily use as a source of calcium. So basically, the clay is partly useful because I do have reactive silica, which is present in the glassy portion. Only it's a smaller fraction of the total silica present in the clay. And I have calcite, which I can use as a source of calcium in the system. Then if I look at sponge iron, even the sponge iron contained silica, but unfortunately a lot of it is locked in the quartz form, which is non-reactive. But it also has this glassy portion, which is shown by the black line, which contains reactive silica. So it does contain reactive silica, which I can use as a source of silica in my system. So these are the primary sources of elements that I can use in the cement production. Here's the actual useful materials that are coming from these raw materials that I used. Lime sludge contains 98.75% calcite, which is calcium carbonate, which I can use. Clay contains 13.97 calcite, which is useful. And the sponge iron contains a small quantity, which is 3.36 calcite. So basically, I'm getting my source of calcium from these. And if you look at the amorphous glassy portion, which I have highlighted below, which contains the reactive silica, clay contains about 27%, and sponge iron contains about 52% of this reactive silica. So I'm basically bringing in reactive calcium and calcium and reactive silica, which I need to produce my calcium silicates. And then the clinker that we produced from the vertical kiln. When we did the chemical composition analysis of this, basically we were able to form tricalcium silicate and dicalcium silicate. And because there was also alumina and iron present in the system, in the source materials, we also formed tricalcium aluminate and also tetracalcium aluminoferrite, the 4 Bourke's compounds. The C3S that formed, and one has to remember, is that C3S, C2S, the C3A and C4AF, the 4 primary ingredients of cement are crystalline compounds. So these are, therefore, you see that each one of them has these distinct signature in the form of peaks in the XRD signature. And from our characterization, we were able to find that our cement had about 35% of C3S and about 31% of C2S. Now, normal cements will have close to 50% of C3S. We were not able to produce that high level of C3S, but C2S was a little higher than normal cements, because in normal OPC, we have about 25% of C2S. But we were now able to produce cements which had calcium silicates. The next step was actually to produce the composite cement, which was take the clinker and actually combine it or blend it with other materials. And the whole objective is to enhance the reactivity of the system, and to increase the reaction product content in the system. I want to produce more calcium silicate hydrate in the system. For that, I have to bring in additional sources of silica into the system. So we know that I can use fly ash. So fly ash has reactive silica. It can be used as a supplementary cementitious material. Slag also contains reactive silica. It's also used as a supplementary cementitious material. So we brought these in, but we used a silicomanganese slag, which is basically a peculiar form of slag, which doesn't find ready use in the cement industry. So we basically used this material as our source. And of course, we had to add in gypsum, because in order to produce OPC with clinker, you have to bring in gypsum. And then we brought in some sodium hydroxide, and this was done in order to enhance the reactivity of fly ash. What sodium hydroxide does is it increases the alkalinity of the system, and that basically dissolves the glassy phase that is present in these materials. And the glassy phase is what contains the reactive silica. So it basically enhances the reactivity of the system. And with this, we produce the Portland composite cement, which contain clinker in addition to a mix of supplementary cementitious materials. Now, of course, we characterize the source materials. The fly ash, of course, as was before, the source had a lot of quartz in it. Quartz is the non-reactive silica, but it also had a good glassy portion, which is shown in the black here, which contains the reactive silica. The slag, silicomanganese slag, has a large amount of this glassy portion, which basically contains the reactive silica in it. So the sources of silica were assured in these reactive materials, and this is the final composition, if you look at it, for the Portland composite cement, when everything was blended together. The final step in the process is to check the chemistry, and this is basically done by understanding the chemistry. One can get into the thermodynamic modeling of the compounds that are produced, and basically one can produce these ternary diagrams to see what would be produced in a system. So I can basically, before I start blending and doing experiments, I can actually start doing numerical experiments to see what is produced in the system. So by playing around with the different compositions, we found that for the Portland cement, Portland composite cement, which is shown in the middle column here, PCC, we were able to produce about 41% of this calcium aluminosilicate hydrate, which is basically the CSH that is required to be produced. And we compared it with the ordinary Portland cement, which is commercially available, grade 43, we found that, well, it is lower than what you get from OPC 43, but we were able to produce a higher amount of CSH in the system compared to what I would get from pure clinker. So therefore, the composite cement actually would give us a higher strength when compared to pure cement. And using this approach, we were actually able to optimize how much fly ash and how much slag needs to come into the system. So with this, then, I just wanted to conclude with this, is that we were actually able to achieve the compressive strengths, which basically started matching what you would get from OPC 43 grade cement at 91 days. It's almost catching up with it. In fact, when we looked at results that we got at 180 days, the strength that we got from the PCC, the Portland composite cement, was higher than the OPC 43. And OPC 43 that we used was a commercially available grade 43 cement. So what I want to stress through this whole exercise is, by understanding the raw materials, understanding the chemistry, we can start producing cements using exclusively waste materials. What we did in this exercise was actually, by understanding the chemistry of the raw materials, utilize 100% base materials and produce a cement that does give us strength. Then, by playing around with the chemistry, we were able to optimize it to achieve the desired properties and the strength that is required to meet the commercial needs, where we can start matching what is already commercially available. So with that, I'd like to conclude and open the floor for questions. I know I've gone through it in a very rapid fire manner, but
yes, sir. But your presentation and this the later part, composite cement part, is new to most of us, and of course you have comprehensively touched the production part and all basics. So I invite participants for a quick round of questions, if any. Sir, seems one question of Pavan Kumawat. Fly ash from the thermal power station is having magnesium silicate, and it is corrosive in nature. Then there is any process to remove it for strengthening the cement? It is in the chat box, sir.
Okay. Okay, so magnesium silicate. Yeah, so removing something from a waste material often is an energy-intensive process, so, and oftentimes not worth it. So one way to do look at replacement strategies is either to bind it in some form so that it is in a becomes less harmful, or minimize the replacement so that one does not have to deal with the harmful effect of it. So these are things that one has to do, but typically removal is energy intensive, so that is not advisable.
Exactly, sir. So as there are no further questions, I propose to close this session, and thank you once again, sir, for sparing time for us, and thank you so much.
Sure.
And we are grateful to you for sparing this comprehensive presentation and guiding us on all the basics, and only these basics will enable us to understand the composite cement production part, which was explained in later one. So thank you very much, sir. Thank you very much.
Sure. Thank you.
Now I request KRS Narayan sir to kindly come. Narayan sir has been involved in the waste plastic use in roads for quite long time. He has been pioneer in the IRC code development and its updation, and of course later on he has experience in CO2 sequestration. So he is a well experienced corporate person. I request Narayan sir to please guide us.
Namaskar.
Namaskar.
Suprabhat. Namaskar. Good morning to all. Firstly, I would like to thank the Rajasthan Technical University Vice Chancellor and foremost Dr. Professor Praveen Agarwal, who reached out to me a month back and saying that this is a conference on sustainability in construction. So I thought it was a very, very apt subject because there are various sustainable initiatives that are happening throughout the world. We all know in cement and concrete, we are concentrating on use of replacements of cement and various types of cement such as LC3 cements and so on and so forth. And also carbon emission reduction, then carbon sequestration. So many activities are happening. I chose a subject which is more important to the day because this plastic waste has become a big menace. And as per the Swachh Bharat mission, as well as the initiatives by the Honorable Prime Minister of India and the government, we need to eradicate littering in the roads, waste plastics which are indiscriminately thrown and littered, and then they are burnt. So there are so much of bad ill effects of burning and waste disposal of plastics. So I thought it was appropriate for me to make a presentation on waste plastics in roads. Though the concept is a very old concept in India, India is a pioneer. Let's understand that for once, India is the leader in waste plastics in roads. Nowhere in the world has so many roads been constructed with waste plastics. Last 2 decades, 20 years. I would like to thank my previous speaker, whom I'm always very fond of, Dr. Subramaniam. It takes back me by 4 years. I think he was the chair of the Bantia Bashir. Bantia is my professor. So Bantia Bashir, Dr. R.N. Riker Memorial second lecture at Bombay. So he was a chair and I was a co-chair. So I, as such, have a lot of respect for Dr. Koluru Subramaniam. So my presentation after this.
I will just intervene, sir. I was also there in that conference and I witnessed to that session, sir.
Oh, thank you.
S.K. Manjrekar ji had organized this.
Yes. So that was dedicated to Professor Nemi Bantia and Professor Bashir, because Bashir was also my professor in the Leeds University. So it was a very good event which we had. So let's come to this. I would like to thank the esteemed resource persons, the ladies and gentlemen, and my friends who are present in this seminar. So my lecture will concentrate on a subject of a marriage between polymer chemistry and civil engineering. All my previous speakers have been speaking about cement and concrete, and this subject is completely different from what is cement and concrete. Though I am a concrete technologist for the last 25 years, in my presentation, I will not speak anything about concrete. So I will be talking about something which is very, very relevant, and then the initiatives of the government, Indian government, as well as throughout the world. We have the World Business Council for Sustainable Development, which is concentrating on recycling. The future of the world is recycling and sustainable materials and technologies. Let me tell you that very, very clearly, that we all need to work on sustainable materials and recycling in whatever engineering fields we are in. So with this, let me share my screen. I think I'm new to this, so you'll have to bear with me for a second.
No issues, sir. No issues.
Open presentation. I do not know because we are into Zooms and other meetings, so you have to slightly guide me. Your entire screen, is it? Can Professor Agarwal please help me out on this tab?
Sir, this is present now. There is a tab present now with arrow upwards.
Yes, I know. Your entire screen, window and tab.
Window, I think, window. Tab goes to if something is open in the internet.
Yes. Can you see this?
Yes, it is coming, sir. It has come,
yes.
Sir. So nice of you, sir.
Thank you. Now, as I said, my lecture would be on multi-layered plastics in roads. sustainable solution which we have been trying to work. And as such, again, thank you to the Rajasthan Technical University, AICTE ATAL program for faculty development. And let me start this presentation with a forward-looking statement. This statement is general statement which we want to always, and I make it a point to speak. There are a lot of assumptions, expectations of future events. So this presentation is based on beliefs, intents, projects, and estimates. So this is a general presentation. My contents will be plastics. Though I'm a concrete engineer, I'm a civil engineer, got not much of knowledge on polymer engineering, but though I have acquired these knowledges basically because it is very, very useful for the type of plastics to be used in roads. Circular economy, plastics to road construction. I will also dwell upon a project done by CRRI with using the first time the waste plastics testing in 2002, 18 years back. The existing code of 2013, IRC SP 98. A case study which I want to talk about multi-layered plastics in roads, the first time in the world as multi-layered plastics being used in roads. I would also talk about the amendment where we are a part of the committee to amend and provide recommendations for improvement with respect to practical feasibility, because practically civil engineering is quite different from the theory which we study in our books. Then the CRRI evaluation of the multi-layered plastic is for the first time in the world. And then the national highways and emphasis on plastic road projects, Vision 2021. And also last but not the least, the carbon dioxide emission reduction, which I'm very, very fond of. Plastics, yesterday. Plastics was just invented in 1862. It's a very, very relatively very new material to be used by mankind. Though there are materials such as metals, glass, and so on and so forth, which have been used for a very, very long time. And this is an excellent substitute for scarce, precious natural resources. And it's gained the popularity or the shortcoming of the other materials, because the other materials are getting depleted, and the use of substitution as a commonplace. Plastics has offered an excellent cost economical substitution. So this has become the foundation of the modern lifestyle for conveniences and comforts in every walk of life. So everywhere in this world, plastics are used extensively as substitutes to various other materials, and also a cost economic solution. Can we really imagine a life without plastics? Today, as we speak, we are working with a plastic instrument called computer. So the body is made of plastic. We have a mobile phone with which we cannot live. It's made out of plastic. We have automobiles which are made of plastic. There's a lot of things. Like for instance, the water bottles are made of plastic. Then the packaging. Plastics. Why plastic packaging is extremely important? It's because that it is one substance one material which makes the dry material stay dry, the wet material stay wet. So this is a very, very innovative invention by mankind. So plastic packaging as well as plastic products have become a very indispensable material on earth today. So we cannot live. And each and every common household would have a sufficient amount of plastics. Almost 60 to 70% of the household consists of plastics in daily use. So we just cannot imagine a life without plastics. You cannot replace these plastics with metals and glass. What images we see today are eyesore images. Like for example, we have on the left-hand side, you will see to your left, you will see littering on the roads. Then you have the landfills everywhere. Then you have marine pollution, which is talked about in a great deal throughout the world. And what National Geography said was in 2050, there could be more plastics than fishes in sea. So that's an alarming situation. We'll have more plastics in the sea than the fishes itself. So this is going to be a mind-boggling problem which we are going to encounter. On the right side, you see the pothole-filled roads. So most of us have gone through the monsoon in various parts of the country. And this is one common sight which we see during the monsoon and after the monsoon. And you have considerable amount of money spent on the repairs. These repairs don't even last for a long time. It lasts only till the next monsoon. And again, we get to repair all these. So these are all eyesores. Not only costs us money by repairing these potholes, this also creates a lot of discomfort while driving, and also a lot of accidents. It is told that the pothole accidents in India far out numbers other types of accidents, in natural accidents which can occur on the road. So the potholes are major concern, major worries for us. Reasons for the change: irresponsible usage, disposal of plastics by us. See, what we do is we use a lot of plastics in our daily life. For example, the bags which we have, the packaging material which we use for our atta, as well as for our basically for our rice and so on and so forth, and even including all your chocolate wrappers and then the biscuit wrappers, as well as chips packets, all these, they are used. Milk packets, for example, that is inevitable. Every day we use a lot of milk sachets, milk packets in our daily use. These are basically rampant overusage, as well as wastage occurs after its use. And what we do is we don't have a responsible way of recycling them or disposing them. So it ends up as littering, non-recyclable. Due to poor waste management, it goes into landfills where they are incinerated, and there is a lot of emissions because of them. Basically, the only solution which the whole world is thinking about is a circular economy. So what is circular economy? It's an alternate to the linear economy, where linear economy is make, use, dispose, and that's it, forget it. Now, circular economy is something where you don't dispose it. Even if you dispose it, you take it back and then recycle it and reuse it. So make, use, dispose, reuse. That's a circular economy which everybody in the world is thinking about, including Indian government. Maximize resources utilization for as long as possible. You should know the shelf life of a material and then try to maximize its life by recycling them. Extract the maximum value for them whilst in use. You need not have use and throw. It is told that PET bottles can be used for at least a minimum of a dozen times. So you don't have to drink water and then litter it or throw it away. Though PET bottles have a very good resale value, which can convert into various other products such as textiles. But we always say you can extract maximum value from them whilst in use. Then recover, regenerate products and materials at the end of each service life. So there is a service life for every material. Recover and regenerate these products in such a way that it can become a part of a raw material for use. For example, waste products can also become a raw material and can replace a percentage of the virgin material. It promotes an economic model to increase resource management efficiency, decrease the impact on the environment, because that's a very, very important thing which we need to concentrate. Of late, in the last 3-4 years, there is a continuous emphasis on recycling of all materials, including glass and metals and plastics. So it can be any material, but the most important thing what we should consider is the impact on the environment. So we need to work across the product's life cycle and ensure that the resource management is efficient. Let me get into types of plastics, because all of us know cement, concrete. Civil engineers are very, very knowledgeable on cement and concrete. I'm going to take you through a little bit of 5 minutes on what are the plastics. We have rigid plastics, which are thermoset material. And we have single layer plastics, which are carry bags and so on, and then multi-layered plastic, which are flexible plastics. So we have only two types of material plastics, that's rigid plastics and then flexible plastics. Rigid plastics are all that you have the percentages of rigid plastics which are available with respect to material properties like high density polyethylene, low density polyethylene. Then you have polypropylene, polyvinyl chloride, and PET, polystyrene, which are others. So these are all the materials which the raw materials which are used to manufacture all types of plastics. Rigid plastics are something which you will not be able to recycle much, basically because these are all rigid materials, and you can probably recycle it, but it takes a lot of efforts to recycle. But what we are trying to talk about is these flexible plastics, which are single layer and multi-layer, which are offering the best possible ways for recycling. Basically because they are all at its end of life solution. For example, it has served its purpose, so it has to be recycled, or it's had to be littered. So to avoid littering, you should be able to recycle them. So single layer plastic consists of all this packaging material, and which is depicted in the picture. And then you have carry bags and so on and so forth. So again, you will have the multi-layer plastics, which are multi-polymers and multi-materials. So multi-layer plastic consists of multi-polymers, which are polyethylene, polypropylene, polyvinyl chloride, and PET, as well as multi-materials such as polymers and aluminium, because there are moisture-bearing barrier materials such as aluminium which are used in packaging also. So if you see chips packet, you will find that most of them would have an aluminium coating in a small film of aluminium to ensure that the moisture doesn't penetrate inside. So you have, in multi-layer plastics, you have multi-polymer materials and multi-materials inside it. Some properties of it, some properties such as thickness and softening point has been mentioned here. We need to look at this chart basically because we are looking at construction of roads. So for construction of roads, there should be a proper choice of polymers. Some polymers which have very high melting point, and there are polymers which are under low melting point or low softening point. These low softening or moderate softening points are the materials that are good enough for road construction. We cannot look at PET, which is around 250 degrees Celsius, possibly for utilizing in road construction, because road construction does require a temperature of around 160 to 165 degrees Celsius when bitumen comes in contact with the aggregates. So these are some of the properties of plastics. Now let me come to multi-layer plastics. Multi-layer plastics is a material which has its life, which has ended its life. So basically, which are all the films that are used for packing of foods. Then you have stretch films used for wrapping bottles, etc. And then we have multi-layer films used for packing shampoo, detergents, and other items. So these are all the plastics which have already had its end of life. So we are trying to provide solutions to the end of life, or else otherwise these form a part of the littering, as well as form a part of the incineration, as well as the landfill, which goes to the landfill. So we know very well that the rigid plastics or other PET bottles have a very good resale value because they are completely recyclable. But these are the materials which are multi-layer plastics has no value. So for example, if you have a kabaddi wala, he comes to pick up plastics. He would prefer to take PET bottles because he has an excellent resale value. But for all these, like these small packaging materials, which are multi-layer plastics, he has no value for it. So he will not be picking it up. So, and these will be littered in any place. So this is what we like to work with to establish its use in road construction. Multi-layer plastics have outlived their reuse, it's difficult to recycle, and then mostly end up in landfills. They consist of carry bags, plastics, the biscuit and the chips wrappers, etc. And they are difficult to collect. As I said, the kabaddi wala, the Radhi fellow will not be able to collect these materials because it doesn't offer any value to him. So what he will do is he'll discard these, and these become littered on the roads. And these materials, generally what happens is these materials are not picked up, littered, and then they get to the landfill because the local municipal body or the corporation picks up these material and sends it to the landfill, and where it gets incinerated, or perhaps goes to the cement plant for use as fuel for the kilns. So these are also very good because these are all binders when heated to high temperatures, and there is no evolution of toxic gases at this temperature. So very good to use. So multi-layer plastics are good to use for various applications. Some of the end of life solutions are the energy in the roads. Energy is what many of the cement plants have been taking this waste plastics, this multi-layer waste plastics in all types of forms. What it does is it is picked up and then it is collected and then transported to the plant where it is used to ignite the fuel, used as fuel to ignite the kilns. And then the energy which is used is propelled to use the manufacture of cement. So, and also the second one is the end of life solution is on the road construction. Some serious issues on durability of roads. Let me come to the durability part of the roads. So far, I have addressed the plastics aspect, the type of polymers, the various types of plastics, as well as the end of life plastics such as multi-layer plating, the plastics. Durability of roads. Cracks, inevitable. Every road has a crack. The life of the road depends on the amount of cracks. There are various types of cracks: longitudinal transfers, settlement, climate-induced shrinkage, and potholes. These are all our common sight today. This is prevalent throughout the country. In every state, every city, every municipality, you will have roads which have cracks, which have potholes, and so on and so forth. Especially during the summer season, you will have thermal shrinkage cracks. And then during the winter season or the cold season, you have rutting cracks as well as the potholes after monsoon season. So these are all inevitable because of the poor quality of construction, poor choice of materials, and the mixed designs. I'm not coming into mixed designs, so on and so forth, because I would like to rest this presentation only with the use of multi-layer plastics in road construction. As a concept, this was done a couple of decades back in Mumbai. This is the first road which was done. In fact, one of the speaker in this resource person would be talking is a pioneer. In fact, so, sorry to say that, he's a pioneer in the field of plastic roads, Dr. IIT. I think he's the speaker tomorrow, I suppose. He would be speaking more on sustainable materials. But in fact, he has been instrumental in putting up close to some 20 to 25,000 kilometers of Pradhan Mantri Gram Sadak Yojana, the National Rural Road Development Authority roads, with waste plastics since the last 20 years. So the concept is you have to find a supply chain for waste plastic to roads, then segregation of the collection. Very, very important to segregate these materials. So we are only interested in these carry bags and the multi-layered films, which are the end-of-life solutions, which provide end-of-life solutions. And these post-consumer, non-recyclable, flexible plastic is then collected. Then they are sent to shredding as per the sizes prescribed by the IRC code. They are shredded, and then what happens is these shredded materials are then mixed with the hot aggregates, and then later the plastic coated aggregates are mixed with the bitumen, and the road is laid as per the conventional process. So this is the concept of plastic to road, which has been prevalent for the last 20 years in India, more than 20 years in India. Why should we use shredded waste plastic? Plastic acts as a very, very good binder. As I said, 120 to 130 degrees Celsius is the softening point. There's no evolution of toxic gases at this temperature. Consumes all types of multi-layered plastic, which are currently not recycled. So it provides an excellent end-of-life solution, an excellent solution to littering as well as landfill and incineration. And the challenge, however, lies in collection and segregation, so which is frequently littered. So all types of flexible films with thickness less than 80 microns can be used, which has been as per the government policy. So all types of packaging materials, multi-layer packagings are less than 100 microns. 80 microns is an average one which you can pick it up. Advantages: you can improve the quality of the road, durability and fatigue life of the road. It has higher resistance. Plastic roads have a higher resistance deformation, resistance to water-induced damages, because the plastic coating on the aggregates would provide as a water barrier from entering the pores or the spaces between the aggregates as well as the material. Improved stability and strength. The Marshall stability is higher. No leaching of plastics. Consumes less than 10% less. 10% of bitumen can be reduced. That's dependent on the mix design. So I would not advocate that at the moment. It depends on the mix design. And each ton of plastic waste avoids the entry of 3,000 kgs, that is 3 metric tons of carbon dioxide into the atmosphere. So there is a reduction in global warming as well as the reduction in the carbon emissions. So these are the advantages, how and why we should use shredded waste plastic. The operation is basically, as I said, you have to segregate it, and then you will have to shred it as per size. A lot of machinery. This is a very, very cheap process. You will get a shredder within a lakh of or 2 lakhs of money. You can shred up to 2 to 3 metric tons per day with these shredders. So they are shredded as per the specification, basically because the specification is important only because that the size of the aggregate is very, very crucial for the performance of the road. So when the size of the aggregates is around 10 to 15 millimeters in size for the top 30 mm seal coat, top 30 mm bituminous coat, you will need to have specifications is around 5 mm size, less than 5 mm of plastic waste shredded material, such that it is able to coat at the temperatures which are warranted at the drum mix plant. So when the aggregate is conveyed through the conveyor, the plastics is also dispensed through it, and then it gets coated during melting process. And once it is coated, then you will find the bitumen. After a few minutes, the bitumen is added through the bitumen dispenser, and is added to the plastic coated aggregate, and then the final mix is transported to the site and laid at 110 to 120 degrees Celsius with a 10-ton roller. But the most important thing, it's easy to use plastics. It's available in a shredded form. It's very, very easy to use them. And but the biggest challenge towards the 20-year concept not taking off so easily, basically, is because of the collection of the waste. Now, we still do not have a great collection system in the country. However, throughout the world, this is being addressed. And today in India, with the Swachh Bharat mission in place, we are trying to address the collection of waste. You segregate the waste into different color bins in such a way that the Raddiwala is able to collect the material, reaches the segregation center, which deploys manpower to segregate the multi-layered plastics, goes to a shredder unit, and then what happens is, after the shredding is done of the multi-layer films, then it can be sent to the site to be mixed with the hot aggregates, and then the road can be laid. So the challenge is basically on the collection system and then the segregation system. Otherwise, we don't have any problems. So basically, because of these two problems, the concept of plastic to road has not gained pace as much as it should have had. Because India being the first country to have ever employed plastic to road concept throughout the world. So even after 20 years, we have still not seen much great activity which has happened around this space. So this is the most important thing which we are trying to address. Swachh Bharat Mission is trying to address it by making presentations with all the regional bodies throughout the country, with every city. And we have certain cities who are role models today. Indore is a role model in plastic to roads. They have an excellent collection system, and we all know very well Indore has won the third time in a row. It has won the best city, the most cleanest city in the country. So there is a lot of activities which are happening there, which are being replicated in other cities also. Let me get to CRRI testing. So this testing was done 18 years back on carry bags. Okay, carry bags are no more prevalent because the country has banned the use of carry bags. So this was the first of its research work which was carried out by the reputed institute CRRI, because the government of India, the Ministry of Roads and Transports and Highways, and the Ministry of Surface Transports depend on the testing of materials to be used in roads by the CRRI. So CRRI did an extensive study on waste plastic bags in bituminous concrete mixes, and these were procured from a supplier, and then they were shredded at the plant and then mixed at this ratio. So this is what it is. I can share these materials, also available in the Google. So you can Google search CRRI testing of waste plastics in 2002. So you will get the entire presentation from there. So this was what was the testing parameters which were set for shredded waste plastics for road construction. And there are impurities. There were a lot of impurities. So what had happened was the waste plastics were cleaned, because these carry bags contained wet waste also. So they were cleaned and dried and so on and so forth, and then shredded. So, and these were all single polymer. They were not multi-polymers. They were only polyethylene or polypropylene, because most of the carry bags are made of polyethylene and a little bit of polypropylene. So these are very, very easy to use material. All you have to do is to collect it, shred it, and then use it for roads, because these temperatures are all around 120 to 125 degrees Celsius as the softening point. So it's very, very easy to use carry bags. So at the moment, we don't have carry bags in place. So we have only to deal with multi-layered plastics. The results and recommendations as such, plastic, the use of waste plastic by 8%, because that's what was fixed as 8%, and based on which the codes were arrived. So 8% was substantially improving the stability and the fatigue life and other desirable properties of bituminous concrete mix under adverse waterlogging. On the left side, the table will show you the improvement in the Marshall stability ratio. It was substantial increase. And then again, the most important thing was the retained stability. Retained stability was very, very good with waste plastic. So it was decided that waste plastics are providing a lot of advantages towards roads, to the road construction methods, as well as a material. It was actually a material which could be recycled, which could also add to the durability. So it was very desirable to use the carry bags, shredded carry bags, as a mix material in the road construction. With which, what had happened was the IRC SP 98. This is the code, with 2013 code, which governs the use of waste plastic in hot bituminous mixes. So thoroughly from 2002 to 2013, there were a lot of efforts. There were a lot of legends who worked on that. To name a couple was a couple of them, Dr. Veeraraghavan from IIT Madras. We had Dr. I.K. Patriya. So, and Dr. Sunil Bose, who was a convener of the committee also. So, and CRRI, of course, CRRI, the entire team of CRRI, all of them worked day and night to put up this concept of plastic roads. Many of these rural roads have been built with plastic roads. So people were very certain that the plastics were giving a lot of advantages and benefits to the improvement of the durability of the road. And then the committee was formed to give a guideline for the use, and then the IRC SP 98 2013 code was derived. Specifications as per the IRC 98 code is the plastic material should conform to the size of 2.36 mm. Should be passing this 2.36 mm and retained by the 600 micron C. So you will have a material which is only 2.36 to 600 micron. That's 0.6 millimeter in size. It would be almost like a grain of sand, probably. So dust and other impurities shall not be more than 1%. So it's very, very difficult to find out any wet carry bag or contaminated carry bag with less than 1% of impurity. So an easy method to determine was impurity to determine the ash content at 600 degrees Celsius. Okay, so all these were put in basically because this was what was thought then in 2012 when the 2013 code came out to practice. These were all thought of. For example, ASTM code, for which the range of the low density polyethylene and the high density polyethylene, the melt flow characteristics were established. Very, very difficult unless otherwise a polymer engineer or a polymer chemistry person got involved in the design of this code. It's very, very difficult. The sources which were classified in the code was LDPE carry bags, sacks, milk pouches, bin lining, that's the waste bin lining, cosmetics and detergent bottles. Then PET, that's polyethylene terephthalate, PET drinking water bottles were specified. Polypropylene bottle caps and closures. These are all rigid plastics. They are not flexible plastics, rigid plastics. So less than 80 micron, less than 100 micron, no, you will not get these PET bottles or polypropylene bottle caps and all these with less than 100 micron. Then polystyrene, that's the coffee cups and the disposable cups which we use to drink coffee and tea. Then polyvinyl chloride, PVC mineral bottles, credit cards. All these were all part of this existing IRC SP98 code. So what happened was the contractors were given this code to use this these types of waste plastics. They started sourcing these plastics, and many of the times they came out with a problem stating that some of the rigid plastics were not melting at 160 degrees Celsius. It was taking around 250, 260 degrees Celsius to melt PET. And of course, PET has a better value in terms of recycling, as well as it has different other great benefits of use in manufacturing textile yarns. But because of this code, they were forced to use such material. And I could see that a lot of places where the roads, plastic roads, a lot of roads had failed also, basically because of the poor quality of raw material which had gone into it, because it was very vague, this code. Challenges, bottlenecks for adoption of that code, basically, you have the code which mentions the shredded waste plastic should melt at the temperature of 160 to 175 degrees Celsius. Carry bags, again banned now. Presently, only multi-layered polymer plastic material is available. Multi-layered polymer plastic generally have a composition of different materials. As I said, it's multi-polymer, then the multi-material, that is polypropylene, polyethylene, PET, aluminum, paper, etc. So the melting points vary from 135 to 265 degrees Celsius. PET, which was mentioned as PET bottles, can be used in the 2013 code, does not melt at this temperature. Because, you know, we are one of the largest polymer companies, petrochemical companies in the world. So we have a very, very strong laboratory which analyzes all types of polymers. And we found that PET was not melting at all. The temperatures at the point of addition of the shredded plastic. So I did a lot of work in traveling to many, many drum mix plants throughout the country. Now, what had happened was, when I went to these drum mix plants, the conveyor belt was discharging the aggregates into the drum mix plant, but I did not find any drum mix plant at the time of entry of these aggregates maintained at 150, 160, 175 degrees Celsius. Most of the plant where I carried a pyrometer with me all along to every site of every big contractor throughout the country, I could find the temperatures were a minimum of 200 degrees Celsius to 250 degrees Celsius. Some plants where I put my pyrometer inside the plant, it was 275 degrees Celsius. So at these points, you will have, when the plastic melts, you will have a lot of poisonous gases which emanate. So this addition, because all of these were fire powered, these are all fuel powered, and then the fire was in direct contact with the aggregates to heat the aggregates and the plastic. Most of the plastics, I assume, would have got burnt completely, would have become carbon, would have become black in color. So we did not find much of these carry bags and things like that getting melted at that temperature at all. So it was not actually, the IRC code was not actually serving the purpose. So to be very frank, so which we took it up with the committee and said, no, you go to the plant, you will know exactly what is the type. They said, no, we wanted them to maintain. There are more than 15,000 drum mix plants in the country. How would you monitor all these plants with respect to the temperatures which they have at the point of addition of these aggregates? It's very, very difficult. Most of them are very old plants too. So, and then PVC. Again, PVC was mentioned in the code, but PVC is not recommended due to emission of poisonous gases. So what was this about? So it was a very vague document. Even we brought it to the attention of the IRC committee last year in 2019 when we went to Delhi. So they have agreed, and with the allied board comprising of the chairman of IRC committee, Dr. Sudhakar Reddy, who had asked us to provide our suggestions and recommendations. We had filled up a few details with respect to the polymers which have to be used. And second very important thing is the consistency in the supply. Now, consistency in the supply of shredded raw material. Who's accountable for it? Now, the contractors, you know very well, the contractors, I do not want to mention the role of the contractors in a poor light, but we all know very well that there has always been a slip between the cup and the lip. So when we talk about mixed design, because I'm a thoroughbred concrete engineer, so I have gone to hundreds and hundreds of sites and to do mixed designs with concrete, with different types of aggregates, with high performance, ultra high performance, fiber reinforced concrete, and so on. I found that whatever mixed design was there on the sheet, which was approved by the client, approved at the point of getting the approval from the third party. For example, IITs were approving the mixed design, but at site, there was a big mismatch between the actual use of these raw materials as per design and as per practice. So consistency, who will give you shredded material of that size? People are putting all types of things inside the road, and then when the road failed, they blamed it on the plastics. Lack of supervision and monitoring of quality control. Who will monitor? For plastics itself, you don't need to monitor cement. Cement carries the IS code on the top of the bag. You have a cement test certificate which is provided by the cement manufacturer. You have your own laboratory which can do work with testing the cement with respect to its setting time and so on and so forth. So you have all those facilities, but for plastics, do you have a laboratory in India at the site which can check the quality of plastics? It's very, very difficult. You can't even, as a civil engineer, I could not, few years back, I could not differentiate between what was polyethylene and polypropylene. Being a civil engineer, a concrete engineer, I'm sure most of the people in this room today would not be able to identify what is polyethylene or what is polypropylene. So this is one thing, and a contractor will not have time to think about what is. He can only see a plastic bottle or a cover. So you can tell him plastic cover or a bottle, a plastic bottle, which is made of PET. So procurement availability as per specifications. You need to procure material. You need to make the material available in each and every site, which was the biggest issue. Even though we had an IRC code, the material was not used in proper way and also not used everywhere. The government had mandated in 2008 and then it mandated in 2017 that plastic waste has to be used within 50-kilometer radius of a city. But how many cities had definitely used these? Not very many used it because of the non-availability of the correct quality of plastic waste to be used in roads. I will touch upon the case study which we did because this is a multi-layered plastic. For the first time in the world has somebody done a real strong work on multi-layered plastic. So multi-layered plastic is a very new concept in the world, and we are working with several foreign bodies to determine what is multi-layered plastics to be used in road construction. This was a sustainability initiative of plastic waste management, Reliance Industries. We did two major projects at Nagothane Manufacturing Division, that is NMD. Nagothane is one of our large plants which is located around 100 kilometers away from Mumbai. So this was a 40-kilometer road which we did completely with shredded multi-layered plastic as per the specification. So what we did was we made sure that all the employees were contributing to this initiative. So all the biscuits and chocolates, by the way, we had 75,000 employees work in our Reliance Corporate Park in Mumbai. So we had so many employees who were accessing foods such as chips and biscuits and chocolate. We ran a campaign that everybody put it inside these bins, and then we took it and then we employed a shredder capacity, a shredder vendor, which we shredded that material, and we employed the exact techniques of IRC and laid all these roads in Nagothane, where we did it inside the plant, we did it in the township road, we had a Poynard Road highway which is maintained by the National Highways. We did that road also along with our corporate park and the helipad which was used by which is being used by the chairman. So we wanted to be very, very sure that whatever we do with multi-layered plastics is beneficial to the company, and then it is largely beneficial with the help of all the testing and standards and things like that, was largely beneficial to the society as well as for the country. Tests which we did, all these basic tests, I would not dwell upon too much on these tests, basically aggregates, tests for bitumen, tests for site samples. All these tests were conducted with due diligence, and then we arrived at a data. So for every 1 cubic meter of concrete, the density of the mix. So this is available. I can provide these details. 2.43 tons of the weight of mix. We added 5.5% bitumen and 8% of shredded waste plastic. So we reduced the bitumen content by 10%. So still maintained 5% by the weight of mix as bitumen. And then 8% of waste plastic as per the IRC code was used in this. And then the road was laid as per the procedure which is here. The plastic enriched bituminous concrete, 30 millimeter thick, used for the top varying course alone. We do not advocate that waste plastic should be used in all the layers of road construction. We are using it only for the layer which is susceptible to the environment and to the traffic conditions. So we made these waste plastics in different material. We classified polyethylene and polypropylene material from the multi-layered plastic. So we found that most, with our research, with our extensive research and knowledge in polymer engineering, we found that PVC was not available in multi-layer plastic. So multi-layer packaging films did not have PEC, very less amount of PET. So we went to analyze the polyethylene and polypropylene inside it, and we shredded to those sizes mentioned. And then whatever PVC waste which was also coming through it was eliminated. That was the external waste which was coming through it. That was eliminated. So the aggregate used was locally sourced from Raigad district, and then as per the requirement of the MORTH standards. The drum mix capacity of 60 metric ton per hour was utilized for manufacturing the plastic coated mix, and then mix was transported to the site conventionally as per whatever the road contractors do, and then was maintained, the temperature was maintained between 120 and 140 degrees Celsius. So before laying, the existing potholes were filled by using this material itself, and then the road was, the top surface was laid. So, and then a tack coat was then applied at the rate of 0.5 kg per square meter by using mechanical bruiser. And then the spreader of crusher dust was followed by cold rolling, ensuring 100% sealing. So we adopted all the policies, that the principles used by the road laying contractors. So we did that. And then after a couple of years, we found out that it was improving the durability road. Basically, because this is a plant which sees close to 150 to 160 trucks every day basis of minimum of 35 metric ton load capacity. And they were all turning. They were all 10-wheeler trucks transporting naphthalene, the monoethylene glycol, and polyethylene terephthalate. So there are a lot of materials which were being transported on a daily basis to the plant. They're very heavy duty trucks, and the rainfall is enormous. Let me tell you, if you people manage to come to Raigad district, you will see the heaviest rainfall. Though I have not gone to Cherrapunji, I have gone to Raigad, which has around 350 centimeters of rain every year. That's only during 3 months of the year. The monsoon is between the mid of June to the mid of September. So you will have 350 centimeters of rain. So we saw the actual use, because every year the roads were being relayed again and again after the monsoon. So we did this to ensure that we have a practical feel about the performance of the road after a year or two. So what has happened is, we managed to ensure that the plastics are actually having a solution. The end-of-life plastics got a solution, and because our township was generating a lot of these multi-layered plastics, we found great use to it. And then we used it for the durability of the road itself. So we had a partial replacement. So that, I think there is a caveat in it. It has to be approved by the competent authority. The mixed designs have to be carried out. The Marshall Stability Index has to be carried out. The tensile strength and the compressive strength has to be carried out to ensure that there is a replacement of bitumen with plastic. So that is left to the competent authority to approve. And since it was our own in-house project, we took a decision that we will use 10% reduced bitumen. So reduced maintenance costs over a life cycle period of roads. Sample study, we covered 15 kilometers of the first thing which we had a complete control of, in the sense that we had the financial statements with us. So we were able to save close to some 81,000 rupees per kilometer. So we were saving, apart from providing a solution to the multi-layered plastics, apart from providing solution to the durability of roads with respect to the non-occurrence of potholes after 2 monsoon seasons, we were also saving 81,000 rupees per kilometer. So this is a win-win situation, because we have a win-win-win ratio in this. So I personally feel, unless we give a cost economic solution which is highly technically worth it, it's going to be very, very difficult for people to utilize or use technology or products in the construction field. We all know very well, when you go to the contractor, first thing they ask is, kitna bachta hai? First thing. So this is a big problem. It's a pandemic. Like COVID, it's a pandemic in the mindset of every contractor in India. How much mujhe kitna bachta hai? So this is the most important thing which we thought we should derive, such that this also becomes profitable for the contractor, so that large scale usage. Any technology will find large scale usage or complete usage only when you start showing, apart from technical benefits, cost economical benefits also. We were able to demonstrate that. Key learnings: not a single pothole. First year we had 350 centimeters of rain. This year we had 375 centimeters of rain. So we have not had a single pothole in the roads. None of them got repaired. Heavy duty multi-vehicle axles are moving. And you know, Reliance, even during this COVID pandemic, there are around 90% of the plant capacity is still functioning. So we are at functioning of 90%. So we have close to 135 metric ton capacity flying every hour in our plant. Lesser consumption of bitumen with plastic addition, no leaching of plastics, this is as per CRRI. Prevents problems of end-of-life plastic like littering, incineration, landfill choking, etc. In this project, we consumed 52,000 kgs, that is 52 metric tons of littered waste plastic was consumed in this, only from our township as well as the nearby areas. We were able to utilize that shredded multi-layered plastics. Reduced cost, as I said, is to be certified by the competent authority. Maintenance cost is definitely going to be very, very less over a life cycle period. I'm told, because in the last 2019 budget, there was an allocation of close to 45,000 crores for the repairs of roads, annual repairs of roads. 45,000 crores to 50,000 crores every year is the government funding for repair of roads. What if we could avoid 1 year's repair charges? We are able to save close to 45 to 50,000 crores to the exchequer, which could be utilized for various other developmental activity with the country. So this was a most important premise which we wanted to make. Some of the case shots. Based on this, as I said earlier, the availability of the material is a big question mark. We don't have. So what we did was, based on all these initiatives which we took, we dared to launch a branded product for shredded waste plastics, the first of its kind in the world. Reroute is its name, and this is to assure quality and correct specifications and availability throughout the country in every Zilla. So this is what it is. We collaborated with the CRRI for testing. We are working with the Indian Road Congress to modify the existing code, working with the National Highways, predominantly with the Executive Committee of the National Highways, in providing a lot of recommendations to them to use plastic waste and to carry out demo projects in the country. We are also involved in some pilot projects which are going to be initiated with the National Highways and others. And to address the dispensing of these shredded waste plastics in roads, we are collaborated with Aman India, which is erstwhile Apollo plant, Aman Apollo. We have tied up with them for auto dispensing of the shredded waste plastic. So for example, we pack it and give it to them, and this is put inside a machine which is connected to the drum mix plant. This will be auto dispensing this shredded waste plastics in there, such that your manual intervention as well as the flying away of these thin waste plastic material in windy conditions don't occur. So we are tied up with them, and one of them is about to set trial at Noida. The one is coming up, another one is coming up before December in the Bombay-Nasik highway. So this will be demonstrated for the first time again in the world. And this will provide a solution for reducing the human effort in dispensing these waste plastics in the road construction. We are also conducting a lot of awareness programs with respect to plastic to schools, to colleges, to various institutions, to various social service bodies, to ensure that these multi-layered plastics are very, very important. Don't throw them away. You can utilize them for excellent road construction and durability of roads. What we have recommended after our meetings in 2019, a proposed amendment to the code, which is likely to be published. So in which we said flexible pouches, Ziploc pouches, heat sealed, all of them have been recommended. And then flexible carry bags, shopping bags, non-woven bags, all these except for black color bags and films have been recommended. Courier bags, bubble wrap films, gift wrappers, agriculture mulch films, all these are recommended. Wrapping pallets, boxes, shrink films, shrink films for wrapping boxes, all of them have been recommended. Again, flexible labels of bottles. For example, you have a Bisleri water bottle, you have a Organo water bottle. All these bottles have labels, flexible labels. Only if they do not have PVC, they have been recommended. So all that also has been littered, has been now placed in front of the committee to approve for use as a shredded waste plastic product for road construction. Products such as file covers, folders, flexi posters, mobile covers, adhesive tapes, photo albums, all these playing cards, for example, and then insulation tapes, all these cover bags for baby clothes are all not recommended, since PVC or high melting polymers are widely used to manufacture these items. Pharmaceutical strips for drugs as well as blister packaging not recommended, since PVC. So we took adequate care to address those materials, polymers which are high melting materials, as well as also emanate toxic gases when they are widely used. So all these materials have been discarded, not recommended for the amendment in the present code. So this is what has provided a lot of benefit to the IRC committee itself, that being one of the world's largest polymer company, petrochemical company, we are able to give them some kind of solutions with respect to choice of polymers. So we restricted ourselves to the polymers which are low melting point and also are littered, as well as do not have any end of life solutions. So we have recommended that. Recent pictures of some roads at Gurugram, Lucknow, and then Bengaluru, as well as Delhi. Some of the roads have been built with waste plastics recently. We have now collaborated with CRRI to provide the first of its kind testing comprehensive testing of shredded multi-layered plastic in the world. So this would become a very, very important article which will be published by the CRRI. And this is the evaluation of shredded waste plastic coating on aggregates. Because we wanted to find out what was the temperature at which the drum mix plant. This is a practical solution which we want to offer. So we wanted to see what temperatures were actually the multi-layered plastics were melting as simulated at the drum mix plants. So we try to simulate one inside the CRR itself. We are working on that. Evaluation of properties of mix with addition of 6 and 8% of shredded multi-layer plastic. We also are evaluating the properties by substitution of bitumen by 6 and 8%. We are also testing scientifically on the leaching of microplastics in subsoil. Technically, there is no leaching, basically because this is employed. This 30 mm top coat is done only on the top of the surface. So whatever the microplastics would find it very difficult to enter the subsoil, because there is close to some 350 to 650 millimeters of subgrade, as well as the grades of soil, as well as the aggregates which are provided as a base layer for the roads construction. So it will find it very difficult, but though scientific research study would be helpful to submit to the government. And then test on emission. There is a lot of issues with respect to NGT, for example, on the pollution in Delhi. So NGT has now told that none of the drum mix plants should be operational in Delhi because of addition to the pollution. So by adding waste plastics, how much of bitumen can be saved, how much of emissions can be saved, and whether plastics are contributing to extra emissions, all that is being studied now scientifically. With these studies, we are going to recommend to the national highways as well as the government of India, Swachh Bharat mission. Everybody is dependent on this test certificate to work on a 50-meter pilot road inside CRRI, which will be most probably funded by National Highways, which CRRI is working with the National Highways to fund this project of piloting a road with MLP to showcase the efficiency or the efficacy of the shredded multi-layer plastic. So by December end, we should have the results as well as the interim report and a pilot report by the next quarter from January onwards, which will follow based on these funds sanctioned by the National Highways. Today, in most of the meetings which is addressed by the Union Transport Minister, he is of a very critical view that the road quality, the construction quality is extremely poor. He has gone on records. It is now a very clear statement from the Union Transport Minister that the quality of road is going to be the most important focus area for the government. So he has constituted various committees headed by various bodies to ensure, various people to ensure that the quality of construction of roads are predominantly very important, and then has to be taken care at most cost. And he has also propagated the use of new products, new technologies for sustainable materials for use in road construction, such that you will have the deployment of various new technologies, deployment of various new products, and also ensure the durability of roads go up. So this is the emphasis by the government of India itself. Because of which in July this year, there is an initiative which has come from National Highways. There is a circular which has been circulated everywhere that everybody should start using waste plastics. So the national highways are already issued guidelines, but not many people had taken use of this. So, but again, this has been issued that they have to target 500 kilometers of service roads of national highways, 750 kilometers of service road using waste plastic for the year 2020-21. So this is one which is very, very crucial for adoption in the national highways and on every national highway roads which are coming out for the 2021 onwards. Vision. The National Highways has just put out a vision last month that eco-friendly highways. While using plastic waste in highway construction, 1 kilometer of 4-lane highway helps in disposal of approximately 7 tons of plastic waste. So 1 kilometer of a 4-lane highway, 4-lane expressway would consume 7 tons of plastic waste. It means to say we are building close to some 40 kilometers of national highways every day. So 40 kilometers of national highways every day would take around 14,000 to 15,000 kilometers. That is approximately close to some a lakh of tons of plastic waste can be disposed through only national highways. There are various other city corporations. There are various National Rural Road Development Authority, PMGSY projects. There are various bodies which are putting up roads on a daily basis, on a monthly basis. So they have targets. They all can start using with the help of this initiative by the national highways. So there is a lot of utilization of waste plastic which will come in the near future. And as engineers, we would like to work with sustainable materials, sustainable technologies, and sustainable products to ensure that our durability of roads become greater. So in fact, quickly, I would like to tell you that, in fact, for 17 years, I was working with fiber reinforced concrete in Reliance Industries before taking up this assignment in Reliance Industries. So I was working with Recron 3 years fibers, which can be used to promote the durability of concrete roads and national highways. We are proud to say we are close to some 3,000 to 4,000 kilometers of national highways has been used with fibers. So fibers definitely give a lot of benefit for concrete road, and waste plastic, shredded waste plastic can give you definitely great benefits for bituminous roads. So eco-friendly highways is the way to go. Reduction in carbon dioxide emissions. As I said, 1 kilometer single lane plastic bitumen road will reduce close to 3 tons of carbon dioxide emissions. CO2 emissions can be reduced by 3 tons for just a kilometer of single lane plastic bitumen road. So we have millions of metric tons of CO2 which has to be destroyed in India. And the Prime Minister was very, very vocal in his statement that the whole country should become carbon emission neutral by another 15-20 years. So we have an ambitious target set over the world, including major economies have set ambitious targets for reducing the carbon emissions to nil in the next 2 to 3 decades. So by using waste plastics, we still, in a large way, reducing the carbon emission, the CO2 emissions to the atmosphere, to the environment. So even for a small 1 kilometer single lane plastic road, it has a reduction of 3 metric tons. So there's a lot of way to go for us. With this, I end my presentation, and just I wanted to rejoinder now that whenever you have chips, when your doctor keeps you fit to have chips as well as chocolates, you have it, but don't throw these, don't litter these. It can be very, very helpful for us to make durable roads. So with this, I thank the management of Rajasthan Technical University, and as well as my dear friend Professor Agarwal for having given me an opportunity to talk. So I leave it the room for questions now, if any.
Thank you very much, sir. Participants are requested to ask their queries.
Yes, sir.
And we are happy to learn that Reliance has used plastics in the helipad being used by its chairman as well. So we have also noted that Reliance is working to produce the reroute, say like standard material which can be used in the road construction and other uses.
Thank you, sir.
One question on chat box, please, may refer. What is the effect of rain on plastic roofs?
Rain.
Yes.
See, it's a very good question, because most of the time what happens is water percolation through roads deteriorate the roads. We all know very well drainage is one of the reasons. Next reason is the water which is stagnant on the road surface, because you don't provide camber or anything. There is, for example, if you have an undulating road, you will have water collection on top of the road. Water will certainly find way through the cracks or the pores and the interspatial layers between two materials inside. For example, aggregates. The aggregates provide an interspatial layer. So what happens is the water percolates through them and then deteriorates the quality of road. What happens is plastics, when they are coated on top of the aggregates do not absorb water. So we have a test report coming in from the CRRI which says the saturated density of aggregates is much lower with plastic coating than without plastic coating. So you will have a water barrier which is created by the plastics coating on the aggregates. So we can safely conclude that there will be very less water penetration, though the amount of water penetration is to be studied now. So we don't have a foolproof data with us to say, but with the availability, or basically the practical look at the roads which have been constructed with plastic waste, have shown that it has not produced any deterioration. It has not deteriorated, because even after very heavy rains.
Thank you very much, sir. Two more questions. One has come: if plastic roads are constructed, then how can water sweeps into ground? Say, I think groundwater recharge. Maybe Geeta Swarup question.
I think Ms. Geeta has asked a question which we don't want to happen. We don't want the roads to become porous. Now, the quality of roads is in such a way that it should be non-porous. So we need to have drainages, which the drainage which has to be provided for the water to drain should be not on the road, but on the sides of the road. For example, if the water percolates through the road, you will have a subsoil issues where there will be a lot of friction which is created by the water passing through the road, which would definitely deteriorate the subsoil as well as lose the bearing capacity of the soil. So we do not want the roads to seep water through it.
Yes, sir. Fanendra Mishra ji has asked, sir, can we construct walls by using plastics mixed in cement mortar?
Wonderful question. In fact, I like that question a lot. Being a cement concrete engineer, so I would love to use waste plastic. But what has happened is it's very difficult to use waste plastic, because it's only 80 micron in thickness. Even if you have a small component of 1 mm or 2 mm in size, it will be very difficult for you to mix a cohesive mix. All you can do, probably what I'm trying to think of doing it, is making small pellets out of this waste plastic, small pellets, grind it in such a way it becomes a rigid material like the grains of sand. And these can be utilized in plastering, but it needs a lot of research work to be done. So it's a very good question. We would like to work, and I personally like to work on this subject. Thank you.
Thank you, sir. Do the toxins wrapped with plastics evaporate with sunlight?
That's another good question. Polypropylene, see, if you are going to subject any polymer to sunlight, it should have a UV coating. There is only one polypropylene material which is less UV resistant compared to any other polymers. All other polymers like polyester, polyethylene, and so on and so forth have very high resistance to UV through the sunlight. Polypropylene needs to be coated with a UV resistant material such that it is not deteriorated by the sunlight.
So I am glad that the participants have shown their interest in the subject, and some queries, if found otherwise afterwards, also I shall forward you on mail, sir.
Thank you, sir. Certainly. And my great pleasure, sir, to interact with everybody.
And definitely, I am very much grateful that I had promised you till 12 noon, but you spared time beyond 12 noon as well to guide us, and so nice of you, sir. Okay, sir. Thank you so much, and
thank you to all. Thank you to all. Namaskar.
Some association with your company as well as your expertise. We shall be in touch, sir.
Definitely, sir. We would like to work with universities, with various people, students, the research scholars, as well as the students, in such a way that these kinds of sustainable materials get utilized more in India. Because when a lot of research happens in universities like yours, it reaches the government much more faster than a private company taking it to the government. So I would like to certainly love to work with university as like yours, with eminent people like you, and also the students as well as the faculty members. I'll be very happy to work with you all, sir. Thank you. Namaskar.
Yes, thank you, Namaskar, and we are very much grateful. And in the afternoon, Chief Scientist from CRI, Sri Guru Vittalji, will join us for fly ash in embankments and fly ash in roads. He has been involved since beginning. So I end this session here itself, and see you all again at 2:50 p.m. today.